Hello there and welcome to Life Beyond Seen, where curiosity drifts slower than the tide and science prefers to whisper rather than shout. Tonight, we're not looking up at the stars or pondering the ticking of time, but gazing downward into the calm, endless blue. Because somewhere in the South China Sea, beneath a surface that seems so ordinary, there's a hole that swallows everything: light, sound, and even certainty. They call it the Dragon Hole, the deepest blue hole in the world, a kind of oceanic doorway that drops farther than any diver can reach. It sits quietly near the Paracel Islands, surrounded by coral reefs and turquoise shallows, almost shy about the mystery it hides. Yet beneath that soft surface is a shaft of darkness that plunges over 300 meters down, a space so deep that sunlight dies long before the bottom comes into view. So, as you listen tonight, maybe ask yourself, where are you right now? How close are you to the ocean? Can you hear it where you are, even faintly? Or is it something you've only ever seen on a screen, flat and harmless, never realizing what waits underneath? If this slow dive into the quiet depths helps you relax or gives your imagination something gentle to hold on to, I'd be so grateful if you liked this video or subscribed. It helps others find this little corner of calm, where science and sleep meet somewhere between curiosity and comfort. Now take a deep breath, let your shoulders drop, and picture the surface of the sea, the way light dances on it, the small hiss of waves brushing coral, and below all that, an opening in the reef like a pupil gazing upward at the sun. That's where we're going. The Dragon Hole, the ocean's secret well. What makes this place so strange isn't just its depth, though that alone is record-breaking. It's the way it seems to resist being fully known. Scientists can measure, map, and send machines where lungs would fail. But even with all our instruments, the Dragon Hole behaves like something ancient, aware of how to keep a few secrets. It's named after the mythical dragon who, according to local legend, lived in its depths. Fishermen told stories of strange currents and missing nets, of bubbles rising from nowhere, of a darkness that seemed alive. In those stories, the dragon wasn't evil or kind. It was simply there, vast, unseen, part of the ocean's old mind. The name stuck long before sonar scans confirmed the hole's staggering depth, and even now, as modern technology peaks deeper than ever before, that mythical weight lingers. Because there's something about the idea of a bottomless pit in the sea that presses at the same part of the human brain that looks up at stars and wonders where space ends. The Dragon Hole lies inside the Yongle Atoll, a ring of coral that forms part of the Paracel Islands. If you look at satellite images, it appears as a patch of impossibly dark blue, surrounded by shallower, almost turquoise waters. The shift in colour marks the edge of the drop, a visual threshold where sunlight stops bouncing off the seafloor and simply falls away. For divers, it's both a temptation and a warning. Blue holes, in general, are vertical caves formed over thousands of years, often when ancient limestone caves on land were flooded as sea levels rose. The Bahamas have the famous Dean's Blue Hole, once considered the deepest, at around 202 meters. The Dragon Hole beats that easily, reaching at least 301 meters and possibly deeper, though even that number carries uncertainty. The farther sensors go, the less reliable they become. Down there, pressure crushes, light vanishes, and instruments drift. It's as if the hole prefers to blur the edges of truth. It helps to imagine how these holes are made. During ice ages, when sea levels were lower, rainwater would seep into exposed limestone, slowly carving out vast cave systems. When the glaciers melted and the seas rose, those caverns flooded. Over time, coral and algae grew around their entrances, softening them into perfect circles. The result is a shaft of water surrounded by living reefs, an opening into geological memory. The Dragon Hole, though, is older than most. The region's limestone dates back tens of millions of years, shaped by ancient reefs long before humans named anything. So when you think about it, the hole isn't just deep in a physical sense, it's deep in time. The water inside has likely been trapped and isolated for ages, creating distinct layers that don't mix easily. That's where the science gets fascinating. Oceanographers studying the Dragon Hole have found that it's not a single continuous column of water, but a series of layers stacked like invisible panes of glass. The topmost layer is warm, salty, and oxygen-rich, a typical tropical sea environment. Beneath that, the chemistry changes. Oxygen fades, temperature drops, salinity shifts. By about 100 meters, the water becomes hypoxic, meaning it can no longer support most life. Below that, at 200 meters and beyond, it's anoxic, devoid of oxygen, heavy with hydrogen sulfide and carbon dioxide. The water there is ancient, unmixed for centuries, possibly millennia. It's a time capsule of Earth's earlier oceans, preserved in silence and darkness. No sunlight, no photosynthesis, no coral, no fish. Just microbial life surviving in chemical shadows. These chemical gradients are more than scientific curiosities. They mark a boundary between two different kinds of ocean, one we know and one we've almost forgotten. In the upper layers you find familiar species, corals, small reef fish, plankton. In the layers below, strange bacteria feed on sulfur instead of sunlight. Some of them might resemble microbes that thrived billions of years ago when Earth's atmosphere lacked oxygen. Studying them could reveal how early life survived in hostile conditions, and maybe even how life might persist elsewhere in the universe. NASA has quietly expressed interest in places like the Dragon Hole for this very reason. To them, it's an analogue for alien oceans, like those hidden beneath the ice of Europa or Enceladus. Imagine that. A quiet sinkhole in the South China Sea, holding clues not only to our own past but to the chemistry of life beyond Earth. If you could dive into it, you'd notice the change almost immediately. At the surface, it's bright, warm, and filled with movement. You'd see small fish darting, the shimmer of air bubbles, the ripple of sunlight breaking into ribbons underwater. Descend a few meters, and the light softens, colours dull. Reds fade first, then oranges, till everything is blue and green. At 50 meters, the warmth gives way to a chill. The walls around you are smooth, carved limestone draped in algae. Then suddenly, you pass into the layer where oxygen thins. Sound becomes hollow. Your ears pick up only your breathing and the distant groan of equipment. By 100 meters, the darkness feels thick enough to touch. The deeper you go, the less sense you have of direction. Up and down lose meaning. Your body's internal compass falters because there's no horizon, no texture, no movement except the faint sway of your own bubbles. It's not just physical depth anymore, it's psychological. The same feeling astronauts describe when they look out into space and realize the scale of silence. Few people have ever gone that far down in the Dragon Hole, and none without mechanical help. Even with advanced diving gear, humans can only reach a fraction of its depth. Beyond about 40 meters, nitrogen narcosis begins to cloud judgment. At 100 meters, the pressure is already 10 times that at the surface. At 300 meters, it would crush an unprotected body instantly. So most exploration happens through remotely operated vehicles, ROVs, small robotic submarines controlled from boats above. These machines carry cameras, sensors, and probes that collect data from the darkness. They found small crustaceans, jellyfish-like organisms, and microbial mats coating the walls, but no large animals. There are no sharks, no fish schools, no coral gardens. The hole becomes a void, like a wound in the sea. And yet, even in that void, life persists in microscopic forms, quietly rewriting what we thought possible. The Dragon Hole challenges more than biology. It also pushes at the edges of geology and hydrology. Beneath the visible ocean lies another world of groundwater, trapped in rock formations, seeping through porous layers. In some places, these hidden aquifers connect to blue holes, creating unseen flows. Researchers suspect that the dragon hole might link to such subsurface systems, feeding or draining water in ways we don't yet understand. That could explain strange fluctuations in salinity and temperature recorded at various depths. It might also mean the hole isn't just a pit, but part of a vast network, an underwater cave system stretching under the seafloor, branching like roots beneath the reef. If that's true, the dragon hole isn't a single mystery, it's an entrance to many. For centuries, the local fishermen didn't need instruments to know it was special. They avoided the area not out of fear, but respect. They said the currents there could change without warning, pulling nets and lines into unseen paths. Boats would drift differently near its mouth. Some claimed to hear low rumbles from below, as if something alive was stirring. Modern instruments later recorded small acoustic anomalies, echoes that don't match the shape of the hole itself. They might be reflections from pockets of gas or from irregular chambers below, but there's something strangely satisfying in not knowing. The dragon may not exist, but the mystery that birthed it does, and perhaps that's enough. If you look at a map of the world's blue holes, you'll notice they often form in clusters in the Bahamas, Belize, the South Pacific. But the dragon hole stands apart because of its scale and isolation. It's not surrounded by many smaller holes, and its depth far exceeds nearby formations. That makes it a geological outlier. Theories suggest it may sit atop a collapsed cave system, or even a fault line that allowed water to erode downward faster than usual. Some scientists compare it to a vertical reef turned inside out, a structure that grows downward instead of up, shaped not by coral but by the slow dissolving of rock. Every drop of rain that fell on that ancient landscape contributed, one molecule at a time, to carving the shaft that now swallows Divers Light's whole. And then there's the way it looks from above. Pilots flying over the South China Sea describe the dragon hole as a perfect circle of indigo ink dropped into turquoise water. From that height it looks small, harmless, almost decorative. But if you know what lies beneath, the view changes. That patch of darkness is the visible top of a chasm that could swallow entire buildings. It's a reminder that the ocean, no matter how mapped or studied, still keeps its surprises close. For every satellite image, there's something hidden just beyond the pixels, waiting quietly for curiosity to return. As you listen now, picture yourself hovering just above the edge of that blue. The water is calm, so still it mirrors the clouds. You could almost forget there's a void below, but then a breeze ripples the surface and the reflection breaks. The hole reveals itself again, that perfect, impossible blue. You can't see the bottom, only the feeling of depth, like standing at the edge of a sky turned upside down. Somewhere down there, sensors hum, currents move slowly, and ancient water lies untouched since long before humans learned to build boats. And as strange as it sounds, that water is still part of the planet's living system. It circulates heat, stores carbon, and exchanges minerals with the layers above. The dragon hole might seem cut off, but it breathes with the rest of the sea in its own slow rhythm. What draws us to such places isn't just the science, it's the feeling they evoke, that quiet pull of curiosity mixed with humility. We like to think of exploration as conquest, planting flags on peaks or diving to record-breaking depths. But in truth, every descent like this is more of a conversation. We go down not to claim, but to listen. The dragon hole speaks in chemistry and pressure, in currents and echoes, and each time we measure it, it reminds us that the planet still holds places where human understanding can't quite reach. That's not discouraging, it's comforting, because mystery is the one resource we never seem to exhaust. So if you're still with me, sitting somewhere warm and dry while the world outside is quiet, think for a moment about that deep blue opening halfway across the world. Imagine the surface of the South China Sea at dusk, the last light fading, and the hole darkening to pure shadow. Somewhere under that surface, microbes are feeding on sulfur. Tiny cameras blink in the dark and the ancient water waits, patient as stone. In that stillness lies a reminder of how vast our world remains, and as the night deepens, we'll keep descending, not just into the dragon hole itself, but into the layers of meaning it holds, the legends, the science, and the pull it exerts on anyone who dares to look too long into its eye. The first time you hear about a hole in the ocean, it sounds like exaggeration, something dreamed up by a storyteller rather than a scientist. A hole, after all, implies emptiness, an absence of something that should be there. But the dragon hole is not empty, not really. It's filled with history, water, salt, and the chemical ghosts of earlier worlds. When researchers first began to study it seriously, what struck them wasn't just its shape or its depth, but how old it seemed. Everything about it, the layers of sediment, the trapped gases, the fossils in the limestone, points back through time to an Earth that barely resembled the one we know. It's strange to imagine that the same hole now swallowing robotic probes might have begun as a dry cave under an ancient landscape where air was thicker, seas shallower, and the horizon entirely different. Every ripple at its surface today is a punctuation mark in a sentence millions of years long. If you could somehow rewind the ocean, pulling the water back the way a tide recedes, you'd see the dragon hole emerge as a kind of scar on the limestone shelf. Long before it was flooded, it was a network of caves carved by rainwater seeping through rock, dissolving calcium carbonate grain by grain. The chemistry is deceptively simple. Carbon dioxide from the air mixes with water to form a weak acid, and over geological timescales, that acid can chew through stone as easily as time wears down memory. During colder eras, when sea levels dropped by hundreds of meters, these caves would have been open to air, echoing with dripping water instead of currents. Perhaps bats nested in them, perhaps small reptiles skittered across the floor, unaware that they were living inside the future throat of an oceanic mystery. Then the glaciers melted, the sea rose, and the cave collapsed inward, creating a vertical shaft. The ocean didn't invade it so much as adopt it, filling it slowly until no trace of the original entrance remained. The rock that frames the dragon hole tells the story more clearly than any myth. It's limestone made of compressed coral, algae, and marine skeletons, layered like pages in an ancient diary. Each layer records a chapter of climate and sea level, written in minerals rather than ink. Scientists can take core samples from nearby reefs and read them almost like tree rings, each band a reminder of warm periods, cold snaps, and shifts in ocean chemistry. What they find is that the region has been underwater, above water, and underwater again countless times. The hole is just the latest expression of that long rhythm. It's easy to forget how dynamic the planet is when we only see it in human lifetimes. The dragon hole is a reminder that geography itself breathes, slowly, deeply, on scales that make our civilizations look like flickers of light. When early explorers of the South China Sea mapped the Paracel Islands, they couldn't have guessed what lay beneath their keels. For centuries, sailors marked the region as dangerous for its reefs and unpredictable weather, not for any sense of vertical threat. It wasn't until modern sonar mapping in the 1990s that the distinct circular depression showed up, an almost perfect geometry amid irregular seafloor contours. Even then, it took years to measure properly. Initial estimates guessed it at around 250 metres deep, then 280, and finally over 300. Every new reading pushed the numbers farther down, as if the hole refused to settle on a final figure. That uncertainty persists because sending instruments to the very bottom is a delicate business. Pressure increases by 1 atmosphere for every 10 metres of depth, so at 300 metres you're dealing with over 400 pounds per square inch, pressing on every surface. Electronics fail. Cables snap. Signals distort. Measuring something that doesn't want to be measured becomes an act of patience bordering on philosophy. It's tempting to think of the dragon hole as a static place, a quiet pit where nothing changes, but that's not the case. Blue holes breathe with the tides. Water circulates if slowly, and the chemical layers shift slightly as storms and seasons affect the upper ocean. At the surface, it can look utterly tranquil, a mirror of sky, but beneath, invisible exchanges happen every moment. Salt mixes, gases diffuse, microcurrents twist down narrow walls. The deeper layers remain mostly isolated, but even they feel the planet's pulse in subtle ways. Vibrations from distant earthquakes, fluctuations in sea pressure from typhoons, the faint tug of lunar tides. When scientists deploy sensors, they sometimes detect low-frequency hums, background noise carried from thousands of kilometers away. The whole is listening to the world, even in its silence. The age of this structure predates almost every modern species in the region. The limestone forming its rim began as living coral tens of millions of years ago, back when the climate was warmer and the continents sat slightly differently on the globe. It's older than the Himalayas, which are still rising from the collision of tectonic plates. It might even trace its lineage back to the breakup of ancient supercontinents, when seas expanded into newly formed basins. Thinking about it that way, the Dragon Hole is less a feature of one ocean and more a surviving relic of multiple Earths, each layered over the last. To stand at its edge today is to stand on the latest surface of a story that began before mammals had become more than nocturnal survivors. When researchers collect sediment samples from the hole's upper ledges, they find fossils of marine organisms that once thrived near ancient shorelines. Tiny shells, coral fragments, microfossils of foraminifera, each one a timestamp of changing seas. Some layers show abrupt shifts in oxygen isotopes, signals of past climate change. Others are streaked with volcanic ash from distant eruptions. It's an archive of catastrophe and calm stored in stone. By analysing these patterns, scientists can reconstruct parts of Earth's climate history with surprising precision. The whole becomes a chronometer, a kind of watery clock measuring not minutes or hours but epochs. In that sense, it's older than time as we use the word. Our clocks tick through seconds. The Dragon Hole counts in ice ages. Its isolation also preserves it. Unlike coastal blue holes that interact with tides and human runoff, the Dragon Hole sits far offshore. Few boats venture there, and even fewer divers. There's no tourist infrastructure, no floating platforms with souvenir stands, no rows of beach chairs. It exists quietly, almost indifferent to human curiosity. In aerial photographs, it's a perfect circle of darkness in a field of luminous shallows. You could fly over it without noticing unless someone told you to look. That anonymity has helped keep it pristine. Its ecosystem, though limited, remains largely untouched by pollution or fishing. It's a rare window into what tropical marine environments might have looked like before industrialization. Studying it isn't just about understanding the hole itself, but using it as a baseline for how oceans function without interference. There's a kind of poetry in how something formed by collapse can become a sanctuary. The roof of an ancient cave falls in, water floods the void, and millions of years later it shelters rare microbial communities that may hold clues to life's origins. Collapse becomes creation. It's a pattern nature repeats often. Stars explode to form new elements. Forests burn to make room for growth. Cliffs erode to shape bays where coral flourishes. The Dragon Hole fits that same rhythm, reminding us that destruction and creation are not opposites, but consecutive lines in the same story. The scientists who study it speak of it with a mix of analytical precision and quiet reverence. They take core samples, measure salinity gradients, calibrate sensors, and yet many of them admit to feeling a strange calm while working there. It's not fear or excitement, but a recognition of scale, the awareness that the hole was here long before them and will remain long after. Local mythology gives the place a soul that science doesn't contradict so much as coexist with. The story of the dragon is one of respect, not conquest. In some versions, the dragon guards the sea's balance, sleeping in the depths to keep storms at bay. In others, It represents the connection between heaven and water, a conduit for spiritual forces. It's easy to dismiss such stories as superstition, but they often contain a kind of intuitive truth. The people who lived and fished near the Paracel Islands knew the sea intimately. They understood its moods, its sounds, its subtle warnings. To them, the hole wasn't a geological curiosity, but a living part of the ocean's character. Calling it the Dragon Hole was a way to give shape to something vast and unknowable. In a way, modern science is doing the same thing, just with different language. When marine geologists compare the Dragon Hole to other formations around the world, they find similarities but also striking differences. The Blue Hole of Belize, for instance, has a clear rim and stable walls, but flattens out into caves at the bottom. The Dragon Hole stays narrow and vertical much deeper, suggesting stronger structural support in the surrounding rock. That hints at differences in how the limestone formed, perhaps denser, more compact layers that resisted collapse. There's also the question of a water composition. Samples taken at depth show unexpectedly high levels of certain trace metals and dissolved minerals, which might indicate underground sources feeding into it. That could mean the hole connects to deeper geological reservoirs, possibly even hydrothermal systems. If that's true, then the Dragon Hole isn't just a sinkhole. It's part of a much larger geochemical machine operating quietly under the sea. The temperature profile of the hole adds another layer of intrigue. Normally, ocean water cools steadily with depth, but in the Dragon Hole sensors have found irregular patterns, pockets of warmer water trapped at certain depths, separated by sharp thermoclines. That suggests minimal vertical mixing, as if each layer has its own microclimate. The stability of these layers allows delicate chemical processes to persist, undisturbed for centuries. Within them, bacteria convert sulfur compounds, recycle carbon, and produce gases that slowly seep upward. In a sense, the Dragon Hole is a laboratory that runs itself, operating on timescales beyond any human experiment. It's not an exaggeration to say it holds information about the ocean's memory, the slow heartbeat of planetary chemistry. Even as we map and model it, much remains speculation. The bottom has not been fully visualized. Some sonar readings hint at a debris cone where rocks and sediments have collected. Others suggest an opening, a continuation into horizontal passages. If those passages exist, they might lead to other caverns beneath the atoll, maybe even connecting to the open sea at different depths. That would make the Dragon Hole part of a hidden network stretching beneath the islands like veins. It's the kind of idea that geologists approach with cautious excitement, because it implies a scale of underwater architecture we've barely imagined. The ocean floor, after all, is riddled with caves and tunnels carved by ancient water flows. What looks like solid ground from above might, in some places, be a honeycomb of hidden spaces. Standing on the deck of a research vessel above it, surrounded by endless blue, it's hard to reconcile that calm surface with what's below. The sea looks the same in every direction. Sunlight glinting off small waves, seabirds circling, the horizon crisp and indifferent. Then you glance down at the sonar screen and see a column of nothing stretching into darkness. That contrast between the visible calm and the invisible depth captures why the Dragon Hole fascinates so many people. It's a reminder that beneath ordinary appearances lie extraordinary realities. The world is full of them. Mountains hide magma chambers, forests hide networks of fungi, the sky hides radiation belts, and the sea hides this bottomless mouth in the coral. Curiosity, it seems, is the only instrument that works everywhere. The hole's ancient origins also make it a natural archive for biological evolution. Trapped within its deeper layers are microorganisms adapted to extreme environments. High pressure, no light, low oxygen. Some of these microbes are unique to the hole, found nowhere else. Genetic sequencing shows that they belong to lineages stretching back billions of years, relatives of bacteria that thrived in Earth's early oceans. They metabolize sulfur and methane instead of oxygen, living off chemical reactions rather than sunlight. Studying them doesn't just tell us how life survives under stress. It gives clues to what life might look like on other planets or moons with subsurface oceans. In a very real way, the Dragon Hole is a bridge between ancient Earth and potential extraterrestrial environments. The past and the future meet in its darkness. There's something humbling in knowing that we've sent probes beyond the solar system, yet the deepest parts of our own oceans remain largely unmapped. The Dragon Hole is a perfect example of that paradox. It's not hidden by distance, but by difficulty. It sits right here on our planet, accessible by boat, and yet it might as well be another world. The more we learn about it, the more it seems to represent not an exception, but a reminder. We live on a planet still mostly unexplored. Every layer of sediment, every unexplored passage, every unexplained current is a line in a book we're only beginning to read. The hole itself doesn't need us to solve it. It's been existing perfectly well for millions of years. But by studying it, we remind ourselves of the value of not knowing everything, of letting mystery coexist with understanding. If you imagine standing again at the rim, water lapping quietly against coral, the air thick with salt, you might sense that age beneath you, the weight of all those years pressed into stone and water. The ocean doesn't keep time the way we do. Its clocks are chemical, its memories geological. The Dragon Hole is one of those memories, a remnant of eras when continents drifted and climates shifted. It's a window into the slow processes that shape worlds. The same processes still unfolding beneath our feet. As the sun lowers and the surface turns from silver to black, you can almost feel that age radiating upward through the water, not as a sound or a sight, but as presence. It's not just a hole beneath the waves, it's the ocean remembering itself. Before every journey into the unknown, there's a pause. That quiet, suspended moment when lungs fill, eyes adjust, and the mind steadies itself against what's coming. For divers, it's literal. A single deep breath before the plunge, before air turns to bubbles and the world above shrinks to a thin shimmer of light. But it's also something older than diving, older than language. The instinct to pause before crossing a threshold. We do it before stepping into a dark room, before saying something difficult, before turning a doorknob that leads somewhere uncertain. That same instinct comes alive at the edge of the Dragon Hole. The surface of the water looks calm, unremarkable even, but underneath it is the longest drop on Earth's oceanic shelf. To cross that line is to enter a space where the ordinary rules of sense and safety begin to thin, replaced by pressure, darkness, and the kind of silence that makes your own breathing sound enormous. The descent begins long before anyone gets wet. A dive into a blue hole like this takes weeks of preparation, each step governed by math and patience. Equipment must be checked, oxygen mixed precisely, safety lines measured and coiled. The deeper you go, the narrower the margin for error. Air itself becomes a challenge. Too much nitrogen causes narcosis, too much oxygen becomes toxic. So divers rely on mixtures like trimix, a blend of oxygen, helium and nitrogen tailored to depth. Even then, the limits are strict. Past a certain point, no human lungs can manage the pressure. Machines take over. ROVs and submersibles become the explorers, their metal shells enduring what our bodies never could. But even the people controlling those machines feel the tension of that first moment when the equipment leaves the light. You're not just sending a camera underwater, you're releasing it into a space that has never seen sunlight since the day the cave collapsed. Standing on the deck above the Dragon Hole, you might not sense any of that drama. The air is warm, the sea gentle, the surface rippling like brushed silk. Yet there's something about the colour that betrays its depth. It isn't the soft turquoise of coral shallows, or the rich navy of open sea. It's darker, heavier, a blue that seems to swallow light rather than reflect it. The edge of the hole appears suddenly, not as a cliff or trench, but as a change in shade. One moment the seafloor is visible, scattered with coral and sand. The next, it vanishes into ink. Divers describe this moment as unsettling, like standing at the lip of a cliff with fog instead of ground below. You know the drop is there, but you can't see how far it goes. Instinct whispers to keep your distance, yet curiosity urges you forward. It's the same pull that's driven humans into caves, mountains and space, an ancient need to look over the edge just to see what's there. When researchers prepare to lower equipment into the hole, the process feels ritualistic. The submersible is lifted by crane, its sensors and cameras blinking to life as technicians run final checks. Every bolt, every cable, every pressure seal matters. One weak link could mean losing millions in equipment, or worse, losing a piece of understanding that might never come back. On deck, the air smells of salt and oil. The crew moves carefully, their voices quiet, not out of superstition but respect. There's a sense that they're about to send something into a cathedral, built by water and time. When the machine finally touches the surface, it rocks gently, then begins to sink. The tether unspools with a low metallic hum, and soon the blue swallows it whole. The only sign of motion is the steady stream of data rising back to the computers above. Numbers, temperatures, chemical readings, and eventually images. Those first images are often deceptive. The upper layers of the dragon hole are clear, filled with plankton and drifting jellyfish. Sunlight still filters through, painting the water in shifting ribbons. The walls are pale limestone streaked with algae. It looks peaceful, even shallow. But a few meters lower, the light fades quickly. Red vanishes first, then orange, until only shades of blue and green remain. Colours that once seemed bright turn ghostly. At around 40 meters, the human eye starts to lose detail. Shadows stretch. Objects appear farther than they are. Then comes the first thermocline, a sharp boundary where warm surface water meets the cold, heavy layer below. You can feel it slide across your skin like a sudden breeze. Below that line, everything changes. The water thickens slightly, movement slow, and sound behaves differently. Your heartbeat feels louder, the bubbles from your regulator rise sluggishly, and the light dims into something closer to twilight. If you've ever swum at night, you know that peculiar blend of calm and unease the ocean can create. It's not fear exactly, but awareness, the realization that you're surrounded by something vast and alive. In the dragon hole, that feeling multiplies. The descent is slow, methodical, and strangely intimate. Every few meters, gauges must be checked, adjustments made. Air consumption increases with pressure. The diver's breathing becomes rhythmic, mechanical, almost hypnotic. In and out, bubbles rising past the mask like small silver coins. It's easy to lose track of time here because every second feels stretched, each movement deliberate. The surface is already a memory, a brighter world receding upward into haze. Ahead lies only the downward path, an invitation into blue that darkens by degrees. At 70 meters, the light begins to fail completely. Even with high-powered lamps, the beam fades within a few meters, swallowed by suspended particles. It's not pure darkness yet, but the world narrows to a small sphere of visibility. This is where many divers turn back, not because they want to, but because their bodies insist on it. The pressure is now more than 8 times that of the surface. Each breath must be measured. The deeper you go, the greater the risk of nitrogen bubbles forming in the bloodstream on ascent, a condition divers call the bends. The descent is the easy part. Coming back up is what kills. So the preparation for every dive into a place like this is not just about going down, but planning every stage of return. How long to pause at each depth, how to let gases leave the body safely, how to resist the impulse to rush toward light. It's a discipline as much as a science, patience in its purest form. Machines don't need patience. but they need precision. The remotely operated vehicles that descend into the dragon hole are equipped with sonar, robotic arms, and sample containers. They send back footage that looks both familiar and alien. The walls are smooth, streaked with mineral deposits. Occasionally something drifts across the camera, a jellyfish, a small shrimp-like creature, or a tangle of organic matter slowly sinking. These glimpses remind us that even in the depths, life finds a way. But the deeper the camera goes, the rarer those appearances become. By 150 meters, almost all visible life has vanished. The water turns cloudy with suspended sediments. Laser grids projected by the submersible show the wall widening slightly then narrowing again. It's not a uniform shaft. It twists subtly, like the inside of a funnel carved by water over eons. And then, at around 180 meters, the sensors detect something unmistakable. The oxygen drops to near zero. This is the beginning of the anoxic zone, a realm where ordinary life can't survive. Here, the only inhabitants are bacteria that thrive on sulfur compounds. These microorganisms form thin films on the rock, turning patches of it pale yellow or white. When disturbed, they release faint plumes of gas, ghostly wisps that drift upward before vanishing. The submersible's lights make them shimmer briefly, like dust caught in sunlight. It's both beautiful and unsettling, a reminder that this environment is utterly indifferent to human presence. The machine continues downward, slower now, its instruments adjusting to the increasing pressure. What lies beyond 200 meters is largely unmapped. Sensors report slight fluctuations in temperature and salinity, hints that water from other sources might be seeping in. Some geologists suspect underground channels connecting to deeper aquifers or to the open sea far away. Others think the lower layers are completely sealed, a pocket of ancient water untouched since before the last ice age. Either way, it's a journey into isolation. Every meter down is a step back in time, into water that remembers climates we've forgotten. If you could bottle it and bring it to the surface, you'd be holding a sample of prehistory. Oceans before industry, before cities, before us. But for all its scientific value, what strikes those who study it most is the emotion of that descent. The first breath before entry, the slow sinking through layers of light and sound, the transition from familiarity to alienness. It's like peeling back layers of consciousness. Divers often describe a sense of humility, even reverence, as if entering a space not meant to be disturbed. The ocean is full of mysteries, but blue holes have a particular stillness. They're not bustling ecosystems like coral reefs or chaotic like open currents. They're quiet. Everything that enters eventually slows, falls, and settles. It's easy to see why so many cultures imagine them as gateways to other worlds, to spirits, to memory. Even with all our instruments and equations, part of the experience remains unquantifiable. The dragon hole is not just deep in space, but deep in feeling. On the surface, as the submersible descends, the ship drifts gently in the current. The crew watches monitors filled with data streams and grainy images. They sip coffee, take notes, murmur quietly. Hours pass this way. Occasionally the tether trembles as if something unseen brushes against it, though that's usually just a current shift. Still, everyone feels it. The weight of being suspended over so much unknown. The human brain, wired to perceive landscapes in 3 dimensions, struggles to imagine vertical emptiness on this scale. You could fit the Eiffel Tower, the Statue of Liberty, and most of a skyscraper in the dragon hole and still not touch bottom. Yet all of that vastness lies hidden under a surface barely wider than a small lake. It's as if the planet folds its greatest mysteries into the smallest spaces. Eventually the submersible begins its return. Data flows upward, light slowly brightens, and the blue turns back toward green, then turquoise. Breaking the surface feels abrupt, almost rude. The roar of air, the slap of waves, the chatter of crew. The world is noisy again. The first breath of open air after such a descent feels sharp, dry, and enormous. That breath carries more than oxygen. It carries awe, relief, and the lingering sense that something unseen has shifted slightly inside you. Because once you've gone even a little way down, you can't look at the ocean the same way again. It's no longer a flat surface, but a volume, layered, ancient, alive in ways you'll never fully map. The Dragon Hole invites that transformation every time someone approaches it. Before each dive or deployment, there's always that moment of stillness, the breath before descent. You stand at the edge of what's known, feel the weight of the equipment or the simple pull of curiosity, and inhale. In that breath, there's both courage and surrender, the willingness to trust the unknown, to let it envelop you, to learn from it without demanding it yield all its secrets. And as the air leaves your lungs, the body begins to sink, slowly at first, then steadily, following gravity's quiet invitation. The light above fades, the water cools, the heartbeat slows, and for a little while, the noise of the world disappears, replaced by the steady rhythm of bubbles rising toward the sky you left behind. Every culture that has lived close to the sea has stories about what lies beneath it. The Dragon Hole was no different long before it earned its scientific title or the attention of oceanographers. The people of the Paracel Islands and the surrounding coasts knew it by other names, names that carried both respect and warning. They called it a sleeping mouth, a gate to the deep world, the place where the sea drew its breath. Fishermen told their children to stay away from it, not because they feared monsters exactly, but because they knew the water there could change character in an instant. The surface might look calm, but nets vanished, and currents would reverse for no reason anyone could explain. Over time, those practical warnings turned into myth, and the myth took the shape of something ancient, a dragon that lived in the hole, watching over the tides. The dragon in Chinese mythology has never been the fire-breathing creature familiar from Western tales. It's older, stranger, less bound by the logic of land. It controls rain and rivers, it coils through clouds, it's a symbol of renewal rather than destruction. To imagine a dragon living in the ocean isn't to picture a beast guarding treasure, but a guardian keeping balance. The sea in that part of the world is unpredictable, and the fishermen who depended on it learned to treat it as a living being rather than a resource. So when storms came without warning or waves tore through nets, it wasn't bad luck. It was the dragon stirring in its sleep. To appease it, they'd offer the first catch of the day, a simple act of respect that had more to do with gratitude than fear. In that sense, the Dragon Hole's myth wasn't superstition at all. It was an old way of acknowledging the ocean's authority. Oral histories in coastal villages around Hainan still carry fragments of those beliefs. Some tell of lights that glow under the water on certain nights, strange green radiance that rises briefly before fading. Others speak of deep rumbling sounds, like thunder trapped underwater. Modern science attributes those to bioluminescent plankton and seismic activity, but it's not difficult to see why earlier generations wove stories around them. When you spend nights at sea, far from land, surrounded by nothing but water and sky, imagination becomes as essential as navigation. The horizon blurs. The line between what's real and what's possible softens. Every glow, every shift in current, every ripple in the moonlight becomes a message. The Dragon Hole, perfectly circular and deeper than anywhere else, was the ocean's most eloquent message of all. Legend said the dragon wasn't alone down there. Some stories described it as one of 9 brothers, each living in a different sea cave or trench, each connected through unseen tunnels beneath the earth. When one stirred, the others felt it. That belief created an early, poetic version of what scientists would later confirm. The seas are connected by hidden flows, by undercurrents that move silently between regions. In the myth, the dragon's movements explain the tides, the storms, and even the occasional disappearance of boats. When someone vanished near the hole, villagers said the dragon had claimed them as messengers to the underworld. It wasn't punishment, it was selection. The sea, in their view, kept its own counsel and occasionally required new voices. Archaeologists have found traces of these stories in temple carvings and scrolls from centuries ago. In one 16th century account, a sailor named Wen Jiu wrote of sailing near the Paracel Islands and seeing the sea boil without wind. He claimed the water opened briefly, showing a glowing column beneath before closing again. He called it a dragon's exhale. Another chronicler described fishermen dropping stones tied to rope in an attempt to measure the depth, only to find the line still descending long after they'd run out. They believed it led to the world's heart, a belief that feels almost literal now that we know how far down it goes. What's remarkable is how the myth always portrayed the dragon as patient and protective rather than vengeful. The danger was not the creature itself, but the arrogance of those who ignored its presence. Centuries later, when modern surveyors arrived with echo sounders and scientific gear, some locals regarded them with quiet skepticism. Not hostility, just a kind of gentle amusement. They already knew there was something extraordinary there. They didn't need machines to prove it. But when the data confirmed that the hole plunged deeper than any other known blue hole, even they seemed impressed. For a moment, the myth and the measurement aligned. The dragon was real, if not in scale and bone, then in depth and significance. The name stuck not because it was poetic, but because it fit. Science could quantify the depth, but the legend captured the feeling of it, the vastness, the silence, the sense of a living presence watching from below. The deeper you look into those old stories, the more they resemble an early form of observation. Without instruments, the fishermen had still noticed patterns, how the water around the hole stayed warmer in winter, how storms seemed to radiate outward from its region, how certain fish avoided the area entirely. They turn those patterns into narrative because that's what humans do when confronted with complexity. We build stories to hold what we can't yet explain. In that sense, the legend of the dragon is an early form of data compression, a way to preserve generations of knowledge about a dangerous and fascinating place in a single image, a creature sleeping beneath the sea, powerful, unpredictable, essential. When divers first explored the dragon hole in modern times, they carried those stories with them. Many of the Chinese researchers who led the early expeditions spoke of feeling the myth in their bones, even as they focused on instruments and coordinates. They described a strange calm when the descent began, as if stepping into a place that had already been named by memory. Some even brought small offerings, coins or charms, to drop into the water before lowering equipment. It wasn't ceremony, just acknowledgement. The sea, after all, has a long memory, and respect costs nothing. That gesture, repeated quietly by scientists and sailors alike, links the modern to the ancient, the rational to the mythical. It's a reminder that exploration doesn't erase wonder, it deepens it. Stories of sea dragons appear across the region, not only in China but in Vietnam, Indonesia and the Philippines. They vary in detail but share a similar tone. The sea is alive and its depths are not empty. In some tales, the dragons communicate through whirlpools and rising mists. In others, they sleep for centuries until great changes in the world wake them. These myths once helped explain natural disasters, earthquakes, typhoons, tsunamis, but they also express something subtler, the sense that human life is small compared to the planet's rhythms. The dragon hole embodies that feeling perfectly. To stand above it is to feel both curiosity and insignificance. It's no wonder our ancestors turned that feeling into a dragon, a creature big enough to contain both awe and fear. The legend even shaped navigation. Sailors would mark the region on their maps not just as a danger, but as a boundary. Crossing it was a symbolic act, like stepping into another realm. They'd pour a little rice wine overboard before passing, a modest offering to ensure safe travel. Those rituals may seem quaint now, but they served a real purpose. They reminded people to pay attention, to treat the sea not as an obstacle, but as a partner that demanded awareness. Modern navigation relies on GPS and sonar, but the principle is the same: humility before immensity. Every sailor, ancient or modern, knows that technology may guide you, but the sea always has the final word. Even as modern research continues, the myth hasn't disappeared. In local festivals, small wooden dragons are still carved and set afloat on the water as symbols of peace. Some villagers tell their children that the dragon in the hole breathes bubbles to keep the ocean alive. When storms come and pass, they say the dragon has turned over in its sleep. It's an affectionate explanation, but one that carries wisdom. The ocean's systems, currents, upwellings, temperature shifts, really do affect weather and climate across the world. The dragon, in its way, still shapes the sky. Every culture's myths begin as metaphors for observation. Volcanoes become angry gods. Lightning becomes divine judgment. Deep holes become sleeping dragons. Yet beneath those metaphors lies respect, a recognition that the world is larger and more complex than we are. The Dragon Hole's legend is one of those rare stories that still fits even after science arrives. The instruments confirm the depth, but the feeling remains unchanged. When a diver descends and the light fades, when pressure tightens against the chest and the water darkens into silence, there's a point where data stops and something older takes over. You don't have to believe in dragons to understand the feeling. You just have to listen to the sea long enough. Sometimes at night, when the water above the dragon hole is perfectly still, the surface becomes a mirror. Stars reflect off it so clearly that you can't tell where sky ends and ocean begins. It's easy to imagine that somewhere below, in that column of dark water, something vast and patient is staring back, recognizing the reflection. The myth says that's the dragon's gaze, waiting for the next storm, the next offering, the next curious traveller brave enough to look into its eye. Whether you call it myth or metaphor, it remains the same. A reminder that beneath every surface, even one as calm as a tropical sea, there's a depth that remembers every story ever told about it. When myth gives way to measurement, it doesn't always feel like a victory. Something is gained, yes. The precision of data, the clarity of maps, the ability to name and compare. But something is also lost, that delicate shimmer of possibility that myth protects. The Dragon Hole is one of those rare places where both still coexist. Long before modern technology revealed its true depth, people already knew it was extraordinary. They described its moods, its movements, its strange power to draw the sea inward. Now sonar arrays, pressure sensors and chemical probes do the same thing, only with numbers instead of stories. But if you listen closely to the way scientists talk about it, you can still hear the old reverence. They measure it not just to map it, but to understand what it means to live on a planet still capable of keeping secrets. The first serious attempts to measure the Dragon Hole came in the early 1990s. The South China Sea had become a focus for marine research, and satellite imagery showed a dark circular patch inside the Yongle Atoll, unlike anything else in the region. At first, scientists assumed it was just a deep lagoon, perhaps 150 or 200 metres down. But early sonar scans told a different story. The signal didn't bounce back when expected. It kept descending, echoing faintly from farther and farther below. The instruments had to be recalibrated. Even then, the bottom remained elusive. That's how the legend began to shift into data, through surprise, through the stubborn refusal of the ocean to match expectation. In 2016, a Chinese research team conducted the most detailed survey yet. Using a combination of sonar mapping, water sampling, and remotely operated vehicles, they confirmed the Dragon Hole reached a depth of at least 301 metres. That made it the deepest known blue hole on Earth, surpassing the famous Dean's Blue Hole in the Bahamas by nearly 100 metres. To appreciate that, you need to imagine lowering a rope longer than 3 football fields straight into a shaft of seawater, so dense that light dies halfway down. The measurements were taken layer by layer, using sensors that recorded temperature, salinity, oxygen and pressure every few meters. The data revealed a stratified structure, a vertical stack of distinct chemical environments sealed from one another by density differences. It was less like a well and more like a stack of miniature oceans, each with its own personality. Those measurements changed how scientists understood blue holes entirely. Before, they were thought to be fairly uniform, aerated at the top, stagnant at the bottom. But the Dragon Hole showed a much more complex system. The top 100 meters behaved like the surrounding sea, rich in oxygen and home to plankton, algae and small fish. Below that, oxygen levels plummeted. By 150 meters, it was almost gone. Beyond 200 meters, the water was completely anoxic, loaded with hydrogen sulfide, methane and other gases produced by microbial metabolism. The deeper sensors went, the older the water seemed to be, with isotopic signatures suggesting it hadn't mixed with the open ocean for centuries. That means the Dragon Hole isn't just deep, it's ancient in its chemistry, a self-contained experiment running quietly under natural conditions since before modern civilization began. Getting those numbers wasn't easy. The pressure at 300 meters is 30 times what we experience at the surface. Every sensor housing had to be specially reinforced. Cables could twist or snap under tension. Water could infiltrate electronics in seconds. Even the simplest task, like lowering a probe smoothly, required precision and calm seas. The team worked from a small research vessel anchored at the edge of the atoll, surrounded by turquoise shallows that gave no hint of the abyss beneath. Each morning they'd calibrate instruments, run checks, and lower the rig. Each night they'd analyse data, looking for patterns in the numbers that might reveal something new. It was tedious work, the kind of science that demands patience rather than spectacle. But to those on board it felt anything but dull. They were mapping something that had never been seen, turning myth into measurable reality one line of data at a time. The results confirmed what the legends had implied all along, that the Dragon Hole behaved differently from the sea around it. The temperature profile, for instance, showed almost no seasonal variation below a certain depth. That means the lower layers are isolated, shielded from the chaos of storms and surface currents. Chemical analyses revealed high concentrations of dissolved inorganic carbon and trace metals, suggesting slow geological processes at work, perhaps even seepage from mineral layers below. Salinity gradients were sharp and stable, forming invisible boundaries that kept the layers from mixing. It was like peeling an onion made of water, each layer distinct yet dependent on the others. The most fascinating discovery was microbial. Samples collected from different depths showed that the Dragon Hole hosts unique bacterial communities not found in the open ocean. Some metabolize sulfur compounds in complete darkness, producing energy without sunlight or oxygen. Others survive on traces of methane, a process more common near hydrothermal vents than in shallow tropical seas. Genetic sequencing revealed entirely new species, microorganisms that may represent evolutionary pathways dating back billions of years. To scientists studying the origins of life, that's a treasure beyond gold. These bacteria live in conditions similar to those that might have existed on early Earth, or perhaps on icy moons like Europa. By studying them, researchers can glimpse what life might look like in alien oceans, and how it adapts to survive in extreme isolation. The deeper layers also preserved gases that hold clues to past climates. Trapped within them are bubbles of ancient air dissolved in water long before industrial emissions altered the atmosphere. Measuring their composition offers a direct record of how Earth's oceans once cycled carbon and heat. It's a way of reading history not in fossils or ice cores, but in chemistry. The Dragon Hole, in this sense, is both a time capsule and a laboratory. It's where the planet keeps a record of its own breathing, undisturbed for centuries. Each descent, each probe, each carefully bottled sample adds another sentence to that record. Yet, even as instruments map and measure, the mystery doesn't vanish. If anything, it deepens. The data raises new questions. Why does the lower layer maintain such unusual stability? Are there unseen connections to underground aquifers or deeper fissures? What prevents total collapse of the structure under such pressure? Every answer opens another door. The whole resists simplification. It refuses to be just one thing, a geological feature, a biological niche, a curiosity. It's all of them at once. That multiplicity is what keeps scientists returning. It's what keeps the story alive even after the legend has faded into data. To bridge the gap between myth and measurement is to accept that the two speak different languages but describe the same feeling. When fishermen said the dragon breathed, they were describing the subtle upwelling of water as temperature and salinity layers shifted. When they spoke of strange noises from below, they were hearing the echo of currents against the walls or the occasional pop of gas escaping from rock pores. Science translates those experiences into equations, but it doesn't make them less wondrous. It simply reveals that the universe's poetry is written in physics as much as in words. The act of measuring something like the dragon hole also becomes a metaphor for human curiosity itself. Instruments lower slowly into darkness, sending back data that must be interpreted, corrected, and understood. Every number is a whisper from a place beyond reach. The patience required to assemble those whispers into knowledge mirrors the patience of the myths that sustained curiosity through centuries of ignorance. Long before computers or satellites, people looked at the same patch of sea and wondered. The difference is only in method, not in motive. Both myth and measurement begin with awe. One of the lead researchers on the 2016 expedition described the moment they realized the hole exceeded 300 meters. The sonar trace kept dropping, faint but consistent. On the monitor, the data formed a thin line descending into blankness. When it finally bounced back, the room went quiet. They weren't just reading numbers. They were witnessing a boundary shift. The ocean had revealed a little more of itself, deepening the known world by another measure. The researcher said later that it felt like the dragon had finally taken a breath. A poetic phrase, perhaps, but one that captures the connection between myth and measurement perfectly. Science, at its best, doesn't replace wonder, it refines it. As technology improves, the dragon hole continues to be revisited. New sensors can operate under higher pressure, new drones can map in 3 dimensions, and new models can simulate how such formations evolve over time. But even as the images sharpen and the data sets grow, the essential experience remains unchanged. Standing at the edge of the hole, watching a probe disappear into the blue, you feel the same quiet anticipation that the old sailors must have felt. You imagine what lies below, not as a list of coordinates, but as a living space with its own rhythm. The ocean may be measured now, but it still feels immeasurable. And so, from myth to measurement, the dragon hole teaches something subtle about knowledge itself. Facts don't destroy imagination. They expand it. The dragon wasn't slain by science. It was translated. What was once a creature breathing under the sea is now an ecosystem, a chemical labyrinth, a geological marvel. The name still fits because the essence hasn't changed. The hole still moves, breathes, and humbles anyone who peers into it. The instruments have simply given us new ways to listen. Even now, as researchers analyse fresh data, new questions ripple outward. Could the hole be part of a larger network of submerged caves? How stable are its chemical layers under rising global temperatures? Does it exchange gases with the atmosphere in ways we haven't yet detected? Each of those questions leads to another descent, another quiet moment when the sea takes something human, curiosity, courage, patience, and pulls it downward into its own rhythm. Myth gave the dragon hole its first story. Measurement gives it continuity. Between them lies the truth that both science and legend have always shared, that the unknown isn't a void to be feared, but a depth to be understood, one careful measurement, and one timeless story at a time. If you've ever watched a diver disappear into deep water, you know how quickly a person can vanish. One kick, two, and the surface ripples close again, leaving only air bubbles rising. The dragon hole magnifies that effect into something almost unreal. Once a body or a probe passes a few meters below the lip, it's gone from sight. The surface remains unbroken, calm and indifferent, while below the descent begins through what looks less like water and more like a slow-falling column of blue air. That vertical emptiness is what oceanographers call the throat, the narrowest part of the shaft that leads downward before widening into hidden chambers. The name fits. The dragon hole doesn't just drop, it swallows, layer after layer, breath after breath. Its throat is both corridor and memory, a slow spiral into pressure and silence. From above, it's easy to forget how enormous the shaft really is. Photographs and satellite images make it look small, a dark coin in the middle of a bright atoll. But the human brain isn't built to understand vertical distance. We imagine depth as a kind of darkness rather than dimension. The dragon hole forces that understanding. Its entrance alone is over 100 meters wide, a mouth that could swallow a city block, and yet it narrows just enough below the rim to funnel everything, light, sound, sediment, into the same downward path. Water moves differently inside it. Currents that flow freely across the open sea slow down at the lip, pulled inward by subtle changes in density and temperature. The surface becomes a membrane between two worlds, one alive with coral and fish, the other a realm of cold stillness. It's not dramatic or violent. The transition happens so gradually that you barely notice until it's complete. When researchers lower instruments, they often talk about the feeling of being pulled. It's not gravity, they're already subject to that, but something psychological. Watching the tether slide endlessly into the blue creates a kind of vertigo. The brain keeps expecting an end, a bottom, a shape to orient against. But there's nothing. Only numbers ticking higher on the pressure gauge. The sensors register steady descent. 1 atmosphere, 2, 3. The rope hums softly. The line of data grows longer. Each meter marks another step away from the familiar physics of the surface world. Down here, time and distance blend. The deeper the descent, the slower everything feels, as if the hole itself stretches moments out the way. Pressure stretches air bubbles. The throat of the dragon hole isn't smooth like a well. It's sculpted, pitted, and unpredictable. The limestone walls twist inward in some places, flare outward in others, shaped by eons of water movement and chemical erosion. Laser scans from submersibles show ridges and ledges where rock has resisted dissolution. In the upper section, the walls are pale, coated in a thin film of algae and calcium deposits. Farther down, they darken, taking on a faint metallic sheen from minerals carried by groundwater seepage. If you shine a powerful light across them, you can see subtle lines, ancient watermarks from times when sea levels were lower, reminders that the ocean once breathed differently. Each mark is a signature of change, a record of when the hole was dry, half-filled, or newly flooded. It's like reading the strata of a canyon, only here the pages rise vertically instead of horizontally. At certain depths, the sensors detect a strange phenomenon, slow oscillations in pressure that don't match surface conditions. They're tiny fluctuations, barely measurable, but they suggest the hole is connected to deeper flows, perhaps through cracks in the bedrock. Those microcurrents could carry water from other parts of the ocean, or even from subterranean aquifers. It's as if the throat inhales and exhales on a timescale too long for us to notice. Some researchers have compared it to the slow rhythm of a lung, a vast geological respiration that has continued for millions of years. That's part of what gives the dragon hole its eerie vitality. It isn't static. It moves, almost imperceptibly, shaped by forces we can't directly observe. The throat also acts as a filter. As water sinks, it passes through zones of changing salinity and density. Each transition traps particles, gases, and organic matter. Over centuries, these layers accumulate into fine sediments that drift along the walls like dust on old furniture. Samples taken from those deposits show microscopic fossils, tiny shells, fragments of coral, pollen grains carried by storms from distant continents. Each particle tells a story of where it came from, how it travelled, and how long it's been buried. By analysing them, scientists reconstruct entire environmental histories, monsoon patterns, volcanic eruptions, even hints of ancient river systems that once flowed into this part of the sea. The throat, in this sense, is an archive. Every grain of silt, every trapped bubble, is a word in the ocean's autobiography. What makes this vertical structure so hypnotic is the way it distorts light. In open water, sunlight scatters evenly, softening into a gradual fade. In the dragon hole, the walls reflect and refract it, bending beams into swirling columns that spiral downward before vanishing. Divers say it feels like sinking through the inside of a glass of ink, where light doesn't simply dim but folds in on itself. The effect is both beautiful and disorienting. Your eyes keep searching for depth cues, shadows, outlines, but there are none. The hole becomes an optical illusion that keeps the mind guessing. It's no wonder early explorers described it as endless. Even with modern technology, the view from a camera at 200 meters looks almost identical to the one at 100. The blue never quite turns to black. It just grows thicker, like a living fabric. Every few meters, the environment changes. Tiny shrimp and small fish appear near the upper edges but vanish by 50 meters. Bacteria colonies form faint streaks on the limestone, marking the transition to darker zones. Then, below the 100-meter mark, motion slows to almost nothing. Particles drift lazily, suspended in water so dense that sinking feels like falling through syrup. The throat narrows slightly, creating a bottleneck where currents converge. Sound behaves differently here too. Even mechanical noises from the submersible above become muted, distorted into low hums that fade quickly. It's the kind of silence that feels physical, pressing against your ears like invisible hands. At 200 meters, visibility collapses. Even high-powered lights reveal only small patches of wall. Below this point, the throat opens into wider chambers, but cameras often can't tell where one ends and the next begins. The pressure exceeds 20 times what it is at the surface. Any air bubble would be compressed to a fraction of its size, and yet, even in this crushing environment, life endures. Filaments of bacterial mats cling to rock, thin and flexible like underwater spider silk. They shimmer faintly in artificial light, feeding on minerals and gases that seep through the stone. It's not the kind of life we usually picture. No movement, no colour, no sound. But it's alive nonetheless, slow and steady as the rock itself. When the first ROVs reached the lower parts of the dragon hole, the data they sent back was strangely inconsistent. Instruments would record slight surges in temperature or salinity, then drop again. Some sensors even failed temporarily, overwhelmed by conditions they weren't designed for. Engineers suspected interference from minerals in the water or the effect of high pressure on electronic components. But among the research team, a quieter explanation circulated. The hole's throat wasn't just a passive structure. It was dynamic, pulsing with unseen flows that defied easy mapping. The idea wasn't mystical. It was simply recognition that the ocean is never still, even in its calmest places. Every hole, every trench, every abyssal plane is in motion, part of a planetary circulation system far older and more complex than any single measurement can capture. The comparison between the dragon hole and a throat isn't just poetic, it's anatomical. Like the human airway, it connects two vastly different environments, one where light and oxygen sustain life, and another where darkness and chemistry rule. It allows exchange, though only in controlled, limited ways. In both systems, balance matters. Disturb the equilibrium, and the whole structure reacts. That's why scientists study it carefully, aware that even small disturbances can alter its internal dynamics. When a submersible descends too fast or releases air bubbles, sensors detect shifts in the surrounding layers. The hull responds immediately, adjusting density and flow. It's not conscious, of course, but the effect is strangely lifelike. To picture the throat's true scale, imagine lowering a skyscraper into it, top first. The tip would vanish within seconds, and by the time the structure's base reached the surface, its top would already be 100 meters down. The blue would swallow it whole, and even floodlights wouldn't help. You'd be left with the eerie certainty that something immense was disappearing into something even more immense. That's the kind of geometry the dragon hole demands, one that makes human proportions meaningless. Even the machines we use to explore it look fragile against that backdrop, small motes of technology drifting in a place carved by water and time. The throat's endlessness is, in part, an illusion created by scale, but it's also a truth about perception. The farther we probe into it, the more we realise that bottom is a relative concept. There's always another layer, another tunnel, another gradient. The deepest readings so far show that the hole ends in a cone of sediment, not an open passage, but even that may not be final. Some sonar scans hint at voids beneath the cone, small echoes that could be side chambers or continuation points. If confirmed, they'd mean the dragon hole doesn't end neatly, but branches inward like a root system, extending into unseen parts of the limestone bed. That's fitting. Nothing in nature ever ends where we expect. Above, on the surface, the sea remains calm, unaware, or perhaps indifferent, to what unfolds below. The ship drifts, waves slap against its hull, and the sun glints off metal instruments. Scientists gather around screens showing graphs and images, translating the silence of the deep into patterns of light. But no matter how much data appears, there's a point where the numbers lose their grip. The human imagination fills in what the instruments can't reach. We picture corridors, caverns, maybe even endless continuation, because the mind struggles to accept finality in something so vast. The throat of the dragon hole invites that kind of thinking. It suggests infinity without needing to prove it. In the end, calling it endless isn't about exaggeration. It's about honesty. Every measurement, every probe, every new technology seems to find more complexity, more depth, more questions. The throat doesn't end because curiosity doesn't. The hole isn't bottomless, but our understanding of it might as well be. The deeper we go, the further the mystery stretches away from us, always just beyond the reach of light. And maybe that's the point. The dragon hole's throat doesn't exist to be conquered or completed. It exists to remind us that some things in nature are vast enough to silence even the instruments built to explain them. What disappears into that blue column isn't lost. It's simply absorbed into the slow, patient rhythm of the planet, where depth and time blur together and every descent feels like the first. Down where sunlight surrenders completely, the water turns into something that doesn't feel like water anymore. It's heavy, still, and cold, its molecules packed tight by the weight above. Light cannot reach this far into the dragon hole, not even the faintest glow trickles down. What exists here is a kingdom without light, a realm that does not depend on vision or warmth. To imagine it properly, you have to unlearn how you think life should look. The plants, the colours, the sense of motion, all gone. What remains is chemistry, patience, and the quiet persistence of living systems that learn to exist without the comfort of a sunrise. At around 200 meters deep, even artificial light from submersibles begins to fade within meters of its source. The beams don't pierce darkness, they reveal it. Each movement of the vehicle stirs up fine sediment that drifts slowly, glowing in the lights like metallic snow before vanishing again. The water here is denser, laced with hydrogen sulfide and carbon dioxide, a combination toxic to most surface organisms. To us, it's a place of suffocation, but for the microbial residents of this world, it's nourishment. They survive by oxidizing sulfur or consuming methane, performing chemical alchemy in total darkness. Every second, these unseen bacteria reshape their environment, converting minerals into energy, building delicate networks of existence on the edge of what we define as life. There are no fish schools here, no coral colonies or colourful sponges, no shells gleaming in the sand. Instead, the walls are coated in a thin, waxy film, a microbial mat that clings to the limestone like an invisible skin. It feels slippery when touched by robotic probes, fragile yet widespread. Genetic analysis of samples from these mats revealed dozens of new species, each specialised for survival in low oxygen, high pressure conditions. Some of them resemble microbes found near deep-sea hydrothermal vents, though there's no volcanic activity here. That suggests these organisms evolved similar traits independently, guided not by heat, but by chemistry. Their lives unfold at molecular speed, invisible dramas written in the slow movement of electrons between sulfur and oxygen atoms. When scientists describe these systems, the language becomes clinical: oxidation, reduction, anaerobic respiration. But there's something profoundly elegant in that simplicity. These microbes are the planet's minimalists. They don't need sunlight or complex ecosystems. They build nothing, consume little, and live indefinitely in balance with their surroundings. If life has a foundation, it looks like this. In the absence of light, energy still finds a path, and where energy flows, life persists. The dragon hole's lower layers are a living museum of that principle, a reminder that biology doesn't begin with beauty, it begins with persistence. The deeper the probe descends, the quieter the instruments become. Sound is dampened by density, and movement slows under pressure. If you could somehow be there, suspended in that black stillness, you'd hear almost nothing. Not the hum of the ship above, not even your own heartbeat. The darkness would swallow everything. But the silence isn't emptiness. It's full of invisible communication. Every cubic centimetre of water carries millions of microscopic exchanges, signals, chemicals, enzymes at work. To us it's an abyss. To them it's home. Pressure too defines this kingdom. At 300 metres, every square inch of surface experiences 30 times the pressure of the air we breathe. The weight would crush metal cans flat and implode glass instantly. Yet the organisms here thrive within it. Their cell membranes are reinforced by unique proteins that prevent collapse. Their enzymes operate only under extreme compression, failing completely at surface pressure. If brought upward, they die, not from lack of light, but from too much freedom. In a way, these beings are prisoners of perfection. They exist precisely where conditions are just right for them, and nowhere else. When robotic arms collect sediment samples from the hole's floor, they often bring up thick, sulphur-rich mud. It smells faintly of rotten eggs, evidence of hydrogen sulfide. Mixed within are microbial colonies that shimmer under microscopes, forming tiny filaments and spheres. Some are covered in metallic coatings, iron, manganese or copper compounds, produced by the bacteria as byproducts of metabolism. To scientists, these structures resemble primitive fossils found in ancient rocks on land, remnants of Earth's earliest microbial mats. That parallel isn't coincidence. The dragon hole mimics conditions thought to exist in Earth's first shallow seas billions of years ago. The oxygen-free chemistry, the mineral interactions, the self-contained ecosystem, all echo a planet just learning to host life. The microbes below us may be living versions of that past, descendants of the same lineages that once transformed the atmosphere and paved the way for complex organisms. Exploring this darkness is like reading the planet's oldest diary, except the ink is chemical and the pages dissolve as you turn them. Instruments measure pH, gas concentration, salinity, and isotopes, building a portrait of how this ecosystem functions. What emerges isn't chaos but stability, a perfectly balanced loop. Bacteria consume hydrogen sulfide, releasing sulfate, which reacts with minerals in the sediment, regenerating the compounds the bacteria feed on. Nothing is wasted. It's an ecosystem that recycles itself endlessly, an elegant demonstration of sustainability that human civilization can only envy. Every now and then, cameras capture unexpected movement, a drifting tendril, a slow pulse, a faint shimmer. Most of these are small crustaceans or worms adapted to darkness, their bodies translucent, their organs barely visible. They move slowly, conserving energy. Some cling to the walls, feeding on the bacterial films. Others hover near chemical gradients, where just enough difference between compounds allows energy to flow. They're fragile, almost ghost-like, living embodiments of efficiency. Even without light, nature finds variety. When data from these depths reaches the surface, scientists cluster around screens in quiet awe. The images are grainy, distorted by the density of the water, but unmistakable. You're looking at an alien world under the same sky. No sunlight, no weather, no sound, yet unmistakably alive. Some researchers have described it as standing at the threshold of another planet, Earth's hidden twin, existing in perpetual midnight. It's why space agencies like NASA and ESA take interest in places like this. They see analogues to extraterrestrial environments, subsurface oceans on Europa, Enceladus, or Titan, where life might survive in similar isolation. The Dragon Hole becomes a test site for the imagination, showing that life doesn't need sunlight or even open space to thrive. It just needs chemistry and time. At such depths, colour loses meaning. In full darkness, there is no blue, no black, no distinction between water and void. The camera's sensors translate the absence of light into grey static, and even that feels insufficient. When researchers review the footage later, they describe it as hypnotic. The slow drift of sediment clouds, the lazy rise of gas bubbles, the eerie stillness that never quite resolves into rest. It's motion without progress, change without direction, and yet that motion has shaped the planet for billions of years. The bacteria living in that darkness influence the global carbon and sulfur cycles, subtle but measurable threads connecting the deepest water to the surface we inhabit. In the quietest part of the ocean, life is still participating in the same planetary dance as the forests and skies above. It's easy to think of this world as hostile, but that's a projection. Hostility requires intent, and the deep ocean has none. It doesn't welcome or reject, it simply is. The conditions we call extreme are to its inhabitants ideal. They've had millions of years to adapt while we can barely survive a few minutes there. When we call it alien, we mean it feels alien to us, not that it is alien at all. The Dragonhole's kingdom without light isn't strange within the context of life on Earth. It's one of the oldest and most enduring kinds of ecosystem our planet knows. If you linger on that thought long enough, it becomes humbling. We live in a thin layer of air and light on a planet mostly covered by darkness and pressure. The surface feels like the whole world, but it's just the film on top. Below that, unseen and unbothered, life goes on, following rules written before our species existed. That realization can feel cold or comforting depending on your perspective. To some, it's frightening to know that the majority of Earth doesn't need us. To others, it's reassuring that the planet remains alive even without our involvement. The Dragon Hole is proof of that independence. In that kingdom without light, time itself seems to slow. Without seasons or daylight, without the cues that shape circadian rhythms, there's no natural sense of before or after. The microbes divide when they must, the chemical reactions flow continuously, and decay and renewal happen simultaneously. It's a timeless equilibrium. When scientists retrieve samples, they're lifting fragments of that eternity into our fast-moving world. For a brief moment, those cells see light for the first time in millions of years, and then they die. It's a stark exchange. The deep gives us knowledge, but never without cost. And yet, even as we disturb it, the whole restores itself. The sediments resettle. The chemical gradients return. The bacteria continue their work as though nothing happened. It's difficult to damage a system that measures time in centuries. Long after our instruments corrode and our ships rust away, this kingdom will still exist, quiet and unlit, breathing in its own slow rhythm. The dragon hole doesn't need to be understood to endure. It has done so for longer than our kind has drawn breath. Above it, the surface shimmers with sunlight, boats drift, and waves whisper against the reef. But that brightness reaches only so far before it's swallowed completely. Beneath it lies the other half of the planet, silent, patient, and unseen. A kingdom without light, but not without life. The deeper you study the dragon hole, the more it becomes clear that what defines it isn't only its depth or darkness, but the delicate relationship between two of Earth's oldest sculptors, salt and stone. Together they built this place, dissolved it, and built it again, shaping it over millions of years with patience that borders on eternity. What we see now, a perfect circle of oceanic blue, is just one snapshot in a long conversation between chemistry and geology. To understand the dragon hole is to listen to that conversation carefully, tracing every whisper of mineral, every grain of salt, every fracture in the limestone that led to the creation of this vertical world. It begins, as so many geological stories do, with rain. Not the kind that passes in an afternoon, but rain that falls for millennia, drop by drop, over tropical land masses that once sat where the Paracel Islands now rise. The atmosphere then carried far more carbon dioxide, and when that gas mixed with rainwater, it formed a weak carbonic acid. That acid seeped through cracks in the rock, dissolving the calcium carbonate of ancient coral reefs. Each drop carved a microscopic channel. Multiply that process by millions of years, and you get a labyrinth of subterranean caves, an invisible honeycomb beneath the crust. Eventually, one chamber collapsed, water filled the void, and gravity did the rest. A hole was born, not by explosion or impact, but by persistence. The sea simply took over what the land had already begun. The stone here is limestone, and limestone has a memory. It forms from compressed coral skeletons, seashell fragments, and algae, solidifying over ages into soft, porous rock. In every layer of the dragon hole's walls, you can find remnants of that earlier ocean life. Fossilized polyps, small shells, bits of algae turned to mineral. They tell of ancient seas warmer and shallower than the ones we know, teeming with creatures that vanished long before mammals appeared. Each layer marks a different chapter in climate and sea level, a long pulse of rising and falling oceans. The rock itself is a kind of calendar, but not one that measures years. It counts epochs, measuring time in coral growth and tectonic drift. When geologists extract samples from the dragon hole's rim, they're not just studying stone, they're reading the autobiography of the planet. Salt plays the other half of this story. The South China Sea is a place of evaporation and renewal, where sun and current continually concentrate and dilute salt. In the dragon hole, those fluctuations build invisible boundaries in the water column, layers that resist mixing, separating the whole into distinct strata. The top layer is lighter and fresher, washed by rain and surface currents. Below that, denser saline water forms a heavy blanket, trapping gases and nutrients. These layers remain stable for years, even decades, maintaining the hole's internal chemistry like a sealed jar. It's a strange kind of equilibrium. From above, the sea looks open and continuous, but beneath the surface it's divided into invisible zones, each one defined by how much salt it holds. In places like this, salt becomes both architect and historian. It crystallizes along cracks in the limestone, sealing some, widening others. As it grows, it changes the rock's texture, leaving behind delicate white veins that glimmer faintly under light. These mineral traces mark where seawater once evaporated, concentrating its dissolved minerals until they turned solid. Over time, as new water filtered through, those veins dissolved and reformed, shifting slowly deeper into the structure. Every vein is evidence of an ancient shoreline or a fluctuation in sea level, a signature of the planet's restlessness. Some of those patterns are still visible along the upper walls of the dragon hole, faint lines etched by chemistry rather than erosion. Researchers studying core samples from the hole found another clue hidden in the salt. Trapped within some crystals are tiny pockets of fluid, micro-bubbles of seawater preserved since the time the crystal formed. When analysed, those droplets reveal the composition of ancient oceans, their salinity, temperature, and even trace elements. It's like holding a sample of seawater from millions of years ago, a tangible piece of time. In those microscopic archives, scientists can track how the planet's chemistry evolved, how ice ages and greenhouse periods altered the balance of salt and mineral across the globe. The dragon hole, in that sense, isn't just a natural wonder, it's a geological library still being read. But salt doesn't just record history, it shapes it. The density gradients it creates are what make blue holes such stable, isolated ecosystems. Without those sharp separations, oxygen and nutrients would mix freely, and the unique chemical environments below would vanish. Instead, the salt layers act like invisible walls, protecting the deep bacterial kingdoms from disruption. That same density difference is also what makes exploring the hole so challenging. Instruments lowered from the surface must cross several layers with different buoyancies. Each boundary bends sonar signals, slows descent, and distorts measurements. To reach the bottom, researchers have to compensate for the changing resistance, adjusting their equipment as they go. Salt protects the mystery, even as it defines it. When the first chemical profiles were taken from the dragon hole, the reading seemed inconsistent. Salinity levels fluctuated unexpectedly, sometimes increasing or decreasing sharply over short vertical distances. Scientists eventually realized that the hole wasn't static, it was slowly breathing. Seasonal changes in the surrounding sea caused faint internal currents that shifted the saline boundaries up and down by a few meters, like the tide of an enclosed ocean. Those subtle movements were enough to alter local chemistry, feeding new nutrients to the upper microbial layers and redistributing sediments along the walls. What looked eternal was, in fact, alive with slow, hidden motion. Stone, for its part, plays a quieter role. It holds the shape of the hole and defines the spaces where chemistry happens. The walls aren't smooth, they ripple and bulge, marked by ancient fractures that run like veins. In some places, mineral stalactites remain, proof that the caves once hung in open air before the sea reclaimed them. These formations, once sculpted by dripping water, now lie motionless, their growth frozen by flooding. To divers and ROV operators, they appear ghostly, the remnants of a world that has since drowned. In others, the limestone has collapsed inward, leaving jagged shelves where a sediment collects. Every contour of the wall is a frozen moment in a long process of dissolution, collapse, and reformation. When scientists compare the mineral makeup of the dragon hole stone to nearby reefs, they find subtle differences. The hole's limestone is denser, with fewer impurities, suggesting it formed under more consistent conditions, perhaps when the region was part of a vast shallow platform before tectonic uplift fragmented it into islands. That density might explain why the hole's throat remains stable despite its immense depth. The rock resists collapse even under immense pressure. It's another quiet cooperation between salt and stone. The water shapes the rock, but the rock holds the water's shape. Without that balance, the hole would have crumbled long ago, filling with debris and losing its form. Sometimes, during calm weather, researchers can lower hydrophones into the hole and record faint noises. The sounds are low, irregular, and almost imperceptible. Tiny pops, groans, and crackles as salt crystals grow or dissolve inside microfractures. It's the sound of the rock itself breathing. Temperature changes cause expansion and contraction. Water seeps in, reacts, and then retreats. These small adjustments happen constantly, invisible to the eye but audible to instruments. It's as if the whole is never fully still, always responding to the subtle chemistry that sustains it. The relationship between salt and stone extends beyond geology. It mirrors the balance between permanence and change, the slow rhythm that defines the planet. Salt moves, stone endures, and together they create structures that outlast civilizations. To think of the dragon hole this way is to see it not as a void, but as an intersection of processes, chemical, physical, biological, all working in harmony. It's a place where the planet remembers how to build itself, grain by grain, crystal by crystal. When divers approach the rim, they often notice the rock feels unusually smooth under their hands, almost polished. That sheen isn't just erosion, it's the result of countless microscopic interactions between saltwater and limestone. Every molecule that dissolves or reprecipitates contributes to that polish, making the walls gleam faintly even in dim light. The whole reflects its own history, a surface shaped by the endless dialogue of minerals. As the submersible ascends back toward daylight, instruments capture the gradual shift in salinity and temperature. The layers merge briefly near the top before dispersing into the wider sea. That blending is temporary, erased by the next calm spell. Soon the boundaries reassert themselves, salt settling where it belongs, stone holding steady beneath. The ocean resumes its quiet order. The secrets of salt and stone aren't spectacular, they're slow, meticulous, and patient. They reveal a planet that works not in bursts but in whispers, where time itself is the sculptor. In the dragon hole, every crystal, every curve of limestone, every invisible current tells a story of change so gradual that it might as well be eternal. Salt moves, stone holds, and between them lies a depth that has been forming since before there were names for oceans at all. When researchers first began studying the dragon hole with modern sensors and submersibles, they didn't expect to find much in the way of life beyond microbes. The chemistry, pressure, and lack of oxygen all argued against it. In theory, complex organisms shouldn't exist below the first 100 meters. By 200, oxygen levels are nearly zero, and the water turns hostile to anything with lungs, gills, or bones. But theory has a way of unraveling under the weight of reality. Cameras began picking up movement. Shapes gliding through beams of artificial light. Flashes of texture. Flickers of motion too deliberate to be debris. The first time it happened, the researchers thought it was a trick of the current. The second time, they adjusted the lenses. By the third, they knew they were looking at something alive. The creatures that shouldn't be there aren't mythical or monstrous. They're small, almost delicate, but their presence defies the rules we've written for life. Some are translucent, their bodies so thin that light passes through them like smoke. Others are pale and soft, lacking pigment or armour, built for a world where sunlight and predators no longer matter. A few move in slow, spiralling patterns, conserving energy in the dense still water. When captured on camera, they don't shimmer or flash. They drift, measured and calm, like thoughts suspended in fluid. It's hard to tell where their bodies end and the water begins. Among the first confirmed inhabitants were small amphipods, shrimp-like crustaceans no larger than a fingernail. They live near the boundaries where oxygen levels drop sharply, surviving in conditions that should suffocate them. Their secret lies in hemahyanin, a copper-based molecule in their blood that binds oxygen more efficiently than the hemoglobin we rely on. These creatures can extract life from trace amounts of gas that would mean nothing to us. They feed on bacterial mats coating the limestone walls, scraping tiny patches clean with microscopic claws. In doing so, they create bare spots that grow back within days, a quiet dance of consumption and renewal. There are also worms, thin as threads, some red, some white, living half buried in sediment. Genetic sequencing showed they belonged to families found near deep-sea hydrothermal vents, thousands of kilometres away. How they ended up in a landlocked blue hole remains a mystery. Perhaps they arrived as larvae carried by currents during storms or glacial shifts. Perhaps they've been here for millions of years, survivors of an earlier ocean that flooded this cave long before humans appeared. The idea that isolated populations can persist in such places isn't far-fetched. Similar ecosystems exist in underwater caves in the Bahamas and the Mediterranean, pockets of life that have evolved independently, forming small self-contained civilizations. The Dragon Hole may host one of the most isolated examples on Earth. Occasionally cameras catch flashes of something larger, tiny fish, no more than a few centimetres long, darting near the edges of visibility. Some appear almost gelatinous, with oversized eyes that reflect light in eerie silver rings. One video from a 2019 expedition showed 3 of them hovering motionless just above a mineral ledge. When the submersible's lights moved closer, they turned slowly, unhurried, and vanished into the murk. Later analysis suggested they might belong to a family of cave-dwelling gobies known to tolerate low oxygen. But none of those species have ever been recorded in this region. Either these fish are highly adaptable travellers, or they represent an entirely unknown population. In an age when satellites map continents and genomes reveal ancestry, discovering something new swimming a few hundred metres beneath familiar waters feels almost impossible. And yet, there it is. There's also evidence of gelatinous plankton drifting in the upper layers, comb jellies and siphonophores whose bodies glow faintly under blue light. These fragile organisms are carried into the hole by surface currents and sometimes trapped by the denser layers below. Once there, they adapt briefly, feeding on smaller plankton before dying or sinking deeper, their remains becoming food for bacteria. It's a miniature food chain sustained not by sunlight, but by accident and chemistry. The ocean has a way of finding balance even in places that seem closed off from the world. What puzzles scientists most is how these creatures manage to navigate the sharp boundaries of the hole's internal structure. Between each layer of salinity and oxygen lies a barrier as real as glass. Cross it too quickly, and the difference in density can disorient or kill. Yet some animals move through them effortlessly, as if attuned to gradients we can't perceive. They linger just below one line and above another, feeding where conditions briefly overlap, where just enough oxygen meets just enough nutrient. Its precision evolved over generations, a delicate choreography written in instinct rather than thought. When specimens are brought to the surface for study, most don't survive. The pressure difference alone is enough to rupture their fragile tissues, even those that make it die quickly once exposed to air and light. The researchers handle them gently, recording every detail before they vanish. It's a melancholy ritual, discovering life only to watch it dissolve. But every failure adds to understanding. Tissue samples reveal genetic codes that link these creatures to distant ancestors, fragments of evolutionary history preserved in the dark. One deep-water amphipod species found here carries genes associated with high-pressure resistance, similar to those found in organisms from the Mariana Trench. That suggests convergent evolution, different paths leading to the same solution. Life, faced with the same pressures, invents the same answers. The discovery of such creatures also reshapes how we define habitability. For centuries, scientists assumed that sunlight was the foundation of life. Photosynthesis powered ecosystems, and without it, nothing could survive for long. Then came the discovery of deep-sea vents, where bacteria fed on chemical energy instead of light. The Dragon Hole takes that idea even further. Here, even the vents are absent, and still, life persists. The energy source is purely chemical, the slow exchange of elements between rock and water, driven by nothing more dramatic than natural imbalance. It's the bare minimum required for existence, yet it's enough. That principle, the ability of life to survive wherever it can find energy, has become one of the guiding concepts for astrobiology. If microbes and small animals can endure here, in a hole on a tropical reef starved of oxygen and light, then life elsewhere in the universe becomes more plausible. Some researchers suspect that what we see is only a fraction of the biodiversity that actually exists inside the hole. Instruments capable of detecting trace DNA have revealed genetic signatures from organisms never captured on camera, fragments belonging to mollusks, small crustaceans, even cnidarians. Whether these species still live there or represent ancient remnants washed in from the open sea remains uncertain. The hole's unique structure acts like a time capsule, preserving biological material long after its source has disappeared. Every sample is a snapshot of both present and past life. There's a poetic symmetry in how the dragon hole challenges our expectations. The creatures that shouldn't be there are reminders that nature rarely obeys human boundaries. Where we see impossibility, evolution sees opportunity. In the absence of light, creatures invent new senses. In the absence of oxygen, they find alternate chemistries. Even at pressures that would crush metal, life finds a way to fold itself small enough, flexible enough to endure. What we call extreme, life calls home. The deeper submersibles go, the more elusive these inhabitants become. Movement grows slower, rarer, and more difficult to interpret. Sometimes the cameras record faint trails in the sediment, curving paths as if something has crawled or slithered across the mud. Other times, small plumes rise suddenly from the bottom, stirred by invisible motions. Whether they belong to living creatures or the byproducts of chemical reactions, no one can say. The hole guards its secrets closely, revealing just enough to keep curiosity alive. In 2021, during one of the most detailed expeditions yet, an ROV captured footage of a translucent organism resembling a bell-shaped jelly, suspended at nearly 250 meters. It pulsed slowly, releasing a faint cloud of bioluminescent particles that spiraled upward before fading. The footage lasted less than a minute before the creature drifted out of the range. Analysis of the video showed that it didn't match any known jellyfish species. Its anatomy suggested a hybrid between siphonophore and medusa, possibly an undiscovered form adapted to low oxygen conditions. The image spread quietly through scientific circles, a ghostly symbol of how much we still don't know. Standing on the deck above, surrounded by sunlight and open sky, it's hard to believe that such alien life exists just beneath. The ocean's surface has always deceived us. It's too calm, too familiar. But below that thin boundary lies a world operating under completely different rules. The dragon hole's inhabitants are proof that life doesn't require our permission to exist. It doesn't even require comfort. It only requires persistence, and that persistence can take any shape it needs. The creatures that shouldn't be there remind us that every definition of possible is temporary. We build them based on what we know, and the ocean quietly erases them. What thrives in the dragon hole isn't a defiance of nature, it's nature continuing without us, writing new versions of its own laws. The deeper we look, the clearer that becomes. What we once called uninhabitable turns out to be merely unvisited. And somewhere down there, in the silence and pressure, in the black water between salt and stone, something moves again, slowly and deliberately, proving that even in the darkest place on Earth, life still chooses to exist. The first thing most people notice about the dragon hole isn't its depth, but its calm. The water above it barely ripples. Even when waves break on the reef nearby, the surface of the hole stays unnervingly smooth, as if protected by some invisible membrane. From a distance, it looks painted onto the sea, perfectly round, perfectly motionless. That stillness is deceptive. Beneath it, every molecule is in motion, shifting under gradients of temperature, salinity, and density. But from the surface, it gives the impression of absolute quiet, a calm so complete it feels unnatural. Scientists studying it call this phenomenon hydrodynamic isolation, but that term doesn't do justice to what it feels like to witness it. It's not just water sitting still, it's the sea holding its breath. The stillness isn't an accident, it's the product of structure. The dragon hole's shape, a narrow throat leading to widening chambers, creates a physical barrier against surface turbulence. When wind or waves pass overhead, their energy disperses along the reef, unable to reach down into the deeper layers. The result is a column of water that remains almost untouched by the surface world. Measurements confirm this, even during monsoon season, when storms churn the South China Sea into chaos. Sensors lowered into the dragon hole record almost no change in temperature or current below the upper 20 meters. It's as if the hole lives by its own rhythm, immune to the pulse of the ocean around it. The upper layer breathes with the weather, but everything beneath stays perfectly composed. That stillness is what makes the dragon hole such an extraordinary natural laboratory. In most parts of the ocean, mixing is constant. Currents bring oxygen from the surface, carry nutrients upward, and erase gradients as fast as they form. Here, the lack of movement preserves those gradients. Each layer of water sits almost completely separate from the others, forming distinct micro-environments stacked vertically like invisible floors of a tower. Researchers studying the hole have identified at least 5 major strata, each with unique chemical signatures. The uppermost is rich in oxygen and organic material. The next, cooler and denser, contains traces of nitrogen and ammonia. Below that lies an anoxic zone filled with hydrogen sulfide. And finally, the deep saline pool, heavier, acidic, and ancient. Each layer behaves like a world unto itself, sustained by chemical exchanges rather than physical mixing. When probes descend through these layers, they record abrupt shifts. Temperature can drop by several degrees within a few meters. Salinity jumps sharply, and dissolved oxygen falls to 0. To a physicist, these boundaries are called pycnocleans, density gradients that resist disturbance. To a biologist, they're barriers between ecosystems. But to the divers and engineers who've seen them in person, they're something else entirely. They're walls you can feel. When you pass through one, your skin senses it first. A sudden coolness, a change in buoyancy. Lights behave differently too, scattering oddly as they hit the new layer. The water seems thicker, heavier, less forgiving. The experience is so pronounced that divers describe it as falling through glass. In this slow, stratified world, time seems to move differently. Chemical reactions that would take hours in open water unfold over weeks or months. Oxygen diffusion slows almost to nothing. Sediments settle in perfect calm, undisturbed for centuries. The stillness becomes a kind of preservation. Organic material that drifts down from above collects in fine layers, creating a continuous record of biological and climatic history. In the sediment cores extracted from the dragon hole, scientists can trace everything from shifts in monsoon patterns to volcanic eruptions thousands of kilometers away. Each layer is a page of stillness, written in dust and plankton instead of ink. The hole's immobility has turned it into an accidental archive. This preservation extends beyond geology. The microbial life that thrives in the lower layers depends entirely on that lack of motion. In most oceans, mixing would bring oxygen and destroy the chemical balance these microbes rely on. Here, stillness is survival. Without currents, without waves, the hydrogen sulfide they feed on remains trapped, concentrated enough to sustain them indefinitely. Their ecosystem depends on stability, not change. The dragon hole is, in effect, an organism of equilibrium, a self-sustaining loop where the absence of disturbance becomes the engine of life. The science of stillness, though, goes beyond biology or physics. It touches on how systems maintain order. In nature, stillness is rarely absolute. Even glaciers move, even stones erode. But in the dragon hole, motion slows to the point where cause and effect almost separate. Processes that elsewhere would appear as change happen here too gradually to notice. Salt diffuses molecule by molecule. Minerals dissolve atom by atom. What we perceive as stillness is simply the speed of time reduced to near zero. The hole is not motionless, it's just operating on a different clock. That realization has profound implications for how scientists understand ocean dynamics. For decades, researchers assumed that deep water always circulates, however slowly. The dragon hole challenges that idea. Its lowest layers may have remained undisturbed for hundreds or even thousands of years. Isotopic analysis of trapped gases suggests water at the bottom may predate major human civilizations. If true, that means we're looking at fluid that hasn't touched the atmosphere since before writing was invented. The stillness of that water is a direct link to ancient climates, preserved in its chemistry. When researchers draw samples, they're effectively opening a time capsule sealed by pressure and silence. Stillness also affects how sound moves. The dense, layered water bends acoustic waves unpredictably. When sonar pings are sent into the hole, they scatter and echo, creating phantom depths and false returns. Some signals loop endlessly, bouncing between layers like voices trapped in an echo chamber. That effect has misled measurements for years, contributing to the myth of bottomlessness. In reality, it's the stillness that plays tricks, sound moving slower, trapped between invisible sheets of density. Even the best instruments can be fooled by a medium that refuses to move. To study this kind of equilibrium, scientists borrow language from physics. They talk about diffusion coefficients, energy gradients, and entropy. But behind those terms lies a simple truth. Systems seek balance. The dragon hole has achieved it so completely that it's become a portrait of equilibrium. It shows what happens when a system stabilizes to the point where energy barely flows. That's not death. It's a kind of perfection. Every atom finds its place. Every reaction proceeds at its minimal necessary pace. In a universe obsessed with motion, stillness becomes the rarest form of order. Of course, the hole isn't entirely immune to change. Storm surges can disturb its upper layers, and temperature shifts in the surrounding sea can nudge the boundaries up or down. But those changes are minor and temporary. Within weeks, the gradients re-establish themselves and the structure returns to calm. Nature, left alone, repairs its own equilibrium. The hole's resilience fascinates oceanographers because it mirrors processes seen on a planetary scale. Earth's climate too seeks balance, sometimes violently, sometimes elegantly. The dragon hole is a microcosm of that constant negotiation between chaos and order. Some researchers studying its thermodynamics have begun to model the hole as a vertical ecosystem in metastable equilibrium. It's a phrase that sounds abstract but means something beautifully simple. A place that has found a way to exist without moving. In that, it offers lessons beyond geology. Stillness, as it turns out, isn't the absence of life or energy. It's their most efficient form. When nothing is wasted, when every reaction balances another, a system doesn't need motion to persist. The hole embodies that principle in water and stone. There's a moment during every expedition when the scientists on deck pause to watch the surface. The instruments have been lowered, the data stream steady, and all that remains is waiting. The water below looks motionless, the sun reflecting off it like a coin. Around them, waves lap, engines hum, wind shifts. The hole, though, remains serene, perfectly circular, perfectly still. It's a quiet so deep that it seems to silence everything around it. The ocean keeps moving, but this patch stays calm, as if the earth itself recognizes the need for a single space of rest. That's the science of stillness. It's not a contradiction to motion, but its complement, the necessary pause that allows systems to endure. Without it, chaos would consume everything. In the dragon hole, we see that principle distilled to its purest form, a vertical sanctuary where the laws of physics slow down just enough for life and time to coexist without conflict. What looks lifeless is full of slow vitality. What seems frozen is quietly alive. The stillness isn't empty, it's complete. And somewhere within that calm where water forgets to move, the planet remembers how to breathe in peace. The ocean does not mark time the way we do. It has no seconds, no hours, no schedules. It moves to gradients and gravity, to tides that have been repeating for billions of years, to the pull of the moon and the weight of air above it. Yet inside the dragon hole, there is something that behaves like a clock. Not a clock of gears or pendulums, but one written into chemistry. A slow, fluid mechanism that measures not moments but ages. Every shift in salinity, every layer of sediment, every bubble of gas rising from the stone below is part of a timepiece that ticks in water instead of air. It's so slow that no human could ever hear it, but it's steady enough to outlast civilizations. The dragon hole keeps time for the planet itself. If you were to lower a sensor into its depths and leave it there for years, you would notice something subtle. The temperature, the density, even the chemical composition all change on rhythms too faint for the human body to detect but clear to an instrument that never sleeps. These aren't random fluctuations. They follow patterns, annual cycles tied to monsoons, decadal oscillations connected to shifting currents, and longer, millennial rhythms that echo the slow heartbeat of the climate. The dragon hole acts as a kind of recorder. Its layers, unmixed and isolated, preserve each of these cycles like grooves on a record, storing information about the world above without ever moving itself. It's one of the few places on Earth where time can be read without the interference of human history. The uppermost layer of water feels the seasons. When the monsoon rains arrive, the surface freshens, lowering its salinity. When dry winds blow from the continent, evaporation makes it saltier and denser. These small shifts cause the boundary between layers to move up or down slightly, like a breathing diaphragm. The hole inhales during the wet season, exhaling when it dries. This rhythm, so faint that it barely registers in daily data, marks one of the dragon hole's smallest cycles. But deeper down, where light never reaches, longer rhythms govern. There, the chemistry responds to global processes, changes in sea level, variations in carbon dioxide, volcanic events that alter the ocean's acidity. Each one leaves a fingerprint that settles quietly into sediment, compressing with time until it becomes part of the geological record. Scientists measure this clock not by sound or motion, but by isotopes. The ratio of oxygen 18 to oxygen 16 in the water reveals temperature and evaporation rates from centuries ago. Carbon isotopes trace the exchange between ocean and atmosphere, showing how much carbon the sea absorbed during different eras. In sediment cores taken from the dragon hole, researchers can see these isotopic signatures stacked one atop another, thin, nearly invisible layers representing hundreds of years apiece. It's not the kind of clock that tells you when to wake up or eat. It's the kind that tells you what the planet was feeling 1,000 years before you were born. Some of the gases trapped in those layers are even older. Bubbles of methane and nitrogen rise slowly from cracks in the rock, formed by the decomposition of organic material buried long before modern humans existed. Each molecule is a relic of vanished ecosystems, tiny ghosts of past climates. By studying the ratios of these gases, scientists can reconstruct how life and chemistry have changed over geological time. It's a way of listening to the past through physics, of hearing the Earth's earlier pulses. The dragon hole becomes a metronome of memory, its stillness preserving the rhythm of ages. The deeper the water, the slower the clock runs. In the lowest layer, where oxygen is gone and pressure reigns, reactions nearly halt. Bacteria there metabolize at rates so slow that an entire generation may take months to divide. For them, time stretches endlessly. A single day of human life might be the equivalent of a century in their microscopic experience. This slow metabolism isn't failure, it's adaptation. In the absence of change, slowness becomes survival. These organisms are part of the dragon hole's timekeeping system, each one a tiny pendulum swinging between chemical states. When you look at their metabolism through the lens of physics, it's clear that they measure time as energy flow. Every chemical bond broken is a tick, every new one formed a tock. Above them, sediments record a different rhythm, the rate at which the world forgets. Particles fall constantly, drifting from the bright surface into the dark column below. They descend through the layers like flakes of memory, carrying traces of life from the shallows, bits of plankton, fragments of shell, dust blown from distant deserts. In the calm of the hole they settle evenly, building a perfect chronology. There's no turbulence to scatter them, no scavengers to disturb the pattern. Each grain lands where it falls and stays there. By counting those layers, scientists can measure not just years, but environmental shifts. Thick layers mean times of abundance, strong monsoons, high productivity. Thin, pale ones mean famine, drought, or quiet oceans. It's not just the planet's chemistry being recorded here, it's its moods. Even the salt has its tempo. The concentration gradient changes imperceptibly over decades, adjusted by the subtle dance of evaporation, rainfall, and current. The transitions between layers creep upward or downward by millimeters per year, maintaining a perfect but dynamic balance. When charted over centuries, those movements look like slow waves, a pulse of salinity rising and falling with climate cycles. The dragon hole doesn't resist time, it absorbs it, translating motion into equilibrium. When researchers model this system on computers, they treat it as a series of connected reservoirs, each exchanging matter and energy at predictable rates. But no simulation can truly capture the patience of the real thing. The dragon hole's clock doesn't tick in perfect regularity. It hesitates, it drifts, it responds to events far beyond its horizon. A volcanic eruption halfway around the world, a shift in monsoon intensity, the gradual warming of the global ocean. Its hands move in increments too small to measure yet too vast to ignore. You can't set your watch by it, but you can measure the age of water and know how long it's been since that molecule last felt the open sky. In that sense, the dragon hole tells time backward as much as forward. There's another kind of timekeeping here, one that doesn't rely on chemistry but on decay. Radioactive isotopes, uranium, thorium, carbon-14, embed themselves in the sediments and water. Each decays at a steady rate, a cosmic clock that never stops. By measuring how much remains, scientists can estimate how long it's been since the sediment was laid down or the water sealed away. The results are humbling. Some layers near the bottom are tens of thousands of years old. The water itself may be older still, isolated since the last ice age. What lies at the deepest point of the dragon hole could be a remnant of a climate so different that human ancestors would not have recognized the planet. To touch that water is to touch history directly, to feel time condensed into a liquid. The dragon hole's clock doesn't keep perfect time, but that imperfection makes it more human. It reminds us that time isn't something that exists independently. It's a relationship between change and perception. In a system that changes so slowly, time almost disappears, yet it's there, woven into every molecule. Scientists call it residence time, the average duration a molecule of water spends before leaving the system. In most parts of the ocean, residence time is measured in months. In the dragon hole, it's centuries. The water doesn't circulate quickly enough to refresh itself. Once a molecule enters, it stays, aging quietly. The hole becomes a vessel of ancient moments, a clock that ticks too slowly for our senses but not for the universe's. Sometimes, late at night on an expedition, when the instruments are running quietly and the sea is calm, the scientist on deck will stare at the monitors displaying the data streams. Temperature, salinity, pH, all changing by decimals too small to seem real. But in those tiny variations lies the story of time passing. Each fluctuation is a movement of the clock, an invisible tick. A storm 1,000 miles away, a subtle shift in current, a drop of rain falling days before, all recorded here, translated into numbers that appear steady only because we aren't patient enough to see them move. To stand above the dragon hole is to stand above one of the slowest clocks on Earth. You can't hear it, you can't see it, but everything inside it is measuring time just the same. The microbes count in chemical reactions, the sediments count in layers, the salts count in gradients, the gases count in decay, and together they form a chorus of precision so slow it feels eternal. The surface may sparkle and change with the wind, but below, the rhythm never falters. The dragon hole keeps its own time, older and wiser than ours, ticking softly in water, counting the centuries one molecule at a time. When you look down into the dragon hole, it's easy to think of it as an empty space, a void carved by water and time. But that's not quite true. It wasn't built by nothing. The hole, like all great structures of the earth, has architects. They're not mythical dragons or divine forces, but quiet, persistent agents that sculpt the planet grain by grain. The architects of the abyss are the same ones that have been reshaping the world since before continents split and oceans were born. They are water, pressure, bacteria, and time, each with its own patient craft, each leaving its signature on the stone. Together they've turned this place into one of the most intricate natural constructions on Earth, a monument to the long, slow intelligence of the planet itself. If you were to rewind the clock far enough, back before the sea flooded this region, you would find a landscape of coral plains and shallow lagoons stretching for miles. Rain fell, collecting in pools, seeping into cracks, dissolving rock as it went. Water doesn't carve like a tool, it persuades. It moves with persistence rather than force. A single droplet seems harmless, but millions over millennia can dissolve mountains. The limestone beneath the ancient reef began to weaken, its mineral bonds slowly undone by acid in the rain. Channels formed, then caverns, and finally chambers large enough to echo. The architects worked invisibly, one molecule of carbonic acid at a time. When the sea finally rose and invaded those hollow spaces, a new kind of architecture took over. The ocean brought weight. Every metre of depth added a ton of pressure per square inch, compacting the rock, squeezing air from the old caves, replacing it with liquid mass. That pressure didn't just crush, it stabilized. The walls of the forming hole strengthened under the weight, becoming more resistant to collapse. The same force that would crush a submarine at these depths is the one that keeps the dragon hole standing. In that paradox lies the genius of natural design. Opposing forces balancing each other perfectly, erosion meeting compression, fluidity meeting solidity. Even today, the water continues its craft. Though we call the hole stable, it's not frozen. The limestone walls are constantly dissolving and reforming at a microscopic scale. Seawater carries carbonic acid, which seeps into cracks, releasing calcium ions that later recombine elsewhere as new mineral deposits. It's a cycle of destruction and creation happening continuously, invisible but measurable. This slow exchange gives the walls their strange, smooth texture, as if the stone has been polished by breath rather than touch. The architects are still at work, sculpting without rest. Among them, microbes play a subtler but no less powerful role. In the oxygen-starved depths, bacteria feed on sulfur and methane, altering the chemistry of the surrounding rock. They etch the stone with acid, changing its mineral structure from within. These microbial masons work slowly, building delicate biofilms that trap minerals and guide crystallization. In some places, they've created thin sheets of gypsum and aragonite, forming shimmering scales along the wall, biological fingerprints preserved in mineral form. Under a microscope, those patterns resemble city grids or branching trees. They are the architecture of life itself, written in stone by creatures too small to see. Where water meets rock, tiny reactions accumulate. A molecule of calcium carbonate dissolves, a new one precipitates. Over millions of years, the result is structure: arches, ridges, hollows, and ledges. Some of them look carved, almost deliberate. They're not the product of chaos, but of repetition. Nature doesn't rush, but it never stops. The dragon hole's shape, so symmetrical from above, hides an interior full of complexity. Laser scans reveal an irregular funnel, twisting slightly as it descends. There are alcoves large enough to fit vehicles, narrow corridors that end abruptly, and slopes where sediment has accumulated like drifts of snow. Every contour is a record of flow, every angle a trace of chemistry. The architects left nothing to chance because chance, given enough time, becomes precision. Pressure adds its own touch to this construction. At hundreds of meters below, where every square centimeter bears tons of weight, even solid rock behaves like a slow liquid. It bends, creeps, and reforms. The walls of the dragon hole have likely shifted over millennia, flowing imperceptibly inward. That slow deformation distributes stress evenly, preventing catastrophic collapse. It's the same principle engineers use when designing domes and arches, curves that redirect force instead of resisting it. The Earth discovered those principles long before we did. In that sense, the dragon hole is both a geological formation and an engineering masterpiece, built not by intention, but by natural mathematics. Every now and then, during dives, submersibles record faint vibrations coming from the depths. At first, these were dismissed as mechanical noise, but detailed analysis revealed patterns, low-frequency tremors that correlate with distant earthquakes, even ones occurring thousands of kilometers away. The hole acts as a resonator, amplifying and storing those vibrations. The energy travels through the ocean crust, bounces off layers, and settles here, where the geometry traps it. It's as if the dragon hole listens to the planet, echoing the heartbeat of tectonic motion. That resonance, subtle and constant, slowly rearranges sediment and gas pockets. The architects of the abyss use not only chemistry and pressure, but sound itself. What holds the structure together is balance. Too much dissolution, and the walls would collapse. Too much deposition, and the opening would seal. But the system maintains itself, guided by thermodynamics, adjusting minutely to temperature and pressure changes. It's a self-correcting mechanism. When warmer, less dense water enters, it triggers chemical reactions that harden the limestone. When colder, denser water settles, it slows dissolution. The hole, in its quiet way, regulates its own existence. That equilibrium is why it has survived for so long, while countless other caves have crumbled. It's a living architecture, constantly restoring its shape. If you could speed up time, compress millions of years into minutes, you would see the dragon hole breathing. Its walls shimmer with minerals dissolving and reforming, its layers shifting like liquid glass. You'd see sediments rising and falling, salt lines pulsing, bubbles tracing invisible paths. The whole structure would seem alive, expanding and contracting with the rhythms of climate and tide. What looks eternal in human time is, in geological time, in motion, a structure constantly under construction. Even the life that inhabits it contributes to the architecture. The bacterial mats coating the limestone secrete sticky biofilms that trap sediments, forming thin crusts. Crustaceans and worms burrow into those films, leaving trails that harden into new patterns. Each creature, however small, alters the shape of its home. Over generations, these interactions sculpt the walls as surely as chemical erosion. The architects aren't separate from the architecture. They are the architecture. To study this process is to confront a scale of craftsmanship beyond comprehension. Human builders measure success in decades, perhaps centuries. Nature measures in millions of years. The dragon hole stands as proof that time is the ultimate engineer. Every curve of its structure, every smooth plane of its limestone, every suspended layer of salt water is an artifact of patience. It's a cathedral built molecule by molecule, without blueprints, without pores. The scientists who map it understand this intuitively. They talk about mineral solubility and pressure equilibrium, but behind the data is admiration. To them, the Dragon Hole isn't just a site. It's a process in motion, an artist still at work. Each expedition adds another snapshot of the ongoing creation, another layer of understanding that barely keeps up with the slow artistry below. If the ocean could think, perhaps it would see itself reflected here, in a single, perfect example of what persistence can build. The architects of the abyss don't rush. They have no deadlines, no need for recognition. Their work is quiet, invisible, and absolute. The Dragon Hole is their masterpiece, still being written, still being shaped, its blue throat stretching down into the deep, as if to remind us that creation doesn't always roar. Sometimes it whispers, and those whispers over enough time carve worlds. If you could drain the Dragon Hole and walk along its walls, every step would take you backward through time. The limestone that lines its throat was once the floor of an ancient sea, a shallow warm ocean teeming with life that no longer exists. Tiny shells, coral fragments, and the calcium bones of vanished creatures lie fused into the rock, their outlines softened but still visible if you shine the right light across them. What we see now as solid stone was once living reef, a landscape of motion and colour long before humans ever thought to name the water above it. The hole is not just a window into depth, it's a window into history. Every mineral, every fossilised ridge, every layer of sediment whispers of seas that came before, oceans that breathed differently, and worlds that lived and died quietly beneath the same sky. The story begins around 130,000 years ago, during a time geologists call the last interglacial period. Sea levels then were higher, global temperatures warmer. What is now the Paracel Islands was mostly submerged beneath a broad tropical platform covered in coral and algae. The reef grew upward towards sunlight, layer upon layer, an architecture built by countless small organisms that never knew they were shaping the future. When ice returned and the seas fell, parts of that reef were exposed to air. Rainwater soaked into it, dissolving the carbonate skeletons and hollowing the ground into caverns. Those caverns waited in darkness for tens of thousands of years until the sea rose again and flooded them. That flooding was the birth of the Dragon Hole as we know it, a rebirth of the ocean inside its own fossilised memory. Inside the limestone, evidence of those cycles remains. The walls bear horizontal lines, ancient shorelines etched by long-vanished tides. Chemical analysis of the rock shows alternating layers rich in magnesium or iron, proof of different environmental conditions, times when the sea was warm and shallow, others when it cooled and deepened. There are even pockets of trapped air sealed inside the stone, tiny bubbles of atmosphere from an earlier planet. When scientists drill carefully into those layers and extract the gas, they find compositions slightly different from modern air. Less carbon dioxide, more oxygen, a reminder of eras when forests and oceans worked together in different harmony. The Dragon Hole is not merely deep, it's old in a way that carries memory. Some of the fossils embedded in its walls belong to species extinct for millions of years. Microscopic foraminifera, spiral shells smaller than a grain of sand, tell of tropical waters richer in nutrients than today's. Corals with growth rings thicker than modern ones suggest slower ocean currents and higher concentrations of dissolved minerals. These remnants are timestamps of ancient climates, silent witnesses to long rhythms of warming and cooling that have repeated for eons. When researchers grind samples of this rock into dust and examine the isotopes inside, they can read the temperature of the sea in which it formed, like decoding a diary written by water. The Dragon Hole's geology becomes a translation of oceanic memory into solid form, but the whispers of ancient seas aren't confined to the stone, they drift in the water itself. The deepest layers of the Dragon Hole are chemically distinct from the surface ocean, suggesting that they've been sealed away for thousands of years. In those layers, the ratios of oxygen, isotopes, dissolved salts and trace gases don't match anything found nearby. That means this water may have originated elsewhere, perhaps from an older sea, trapped beneath the Earth's crust during the last glacial retreat, now slowly seeping upward through the limestone. Each molecule carries the signature of the ocean it once belonged to. To study that water is to taste the past directly. The isotopic fingerprints tell stories of changing worlds. During ice ages, vast amounts of water were locked in glaciers, lowering sea levels and concentrating salts in the remaining oceans. The trapped water in the dragon hole retains that higher salinity, its chemistry frozen in time. When the glaciers melted, the surface oceans diluted again, but the deep layer here remained untouched, isolated by density barriers. In effect, it's a liquid fossil, preserving the flavour of a vanished Earth. Sampling it is like drawing a sip from a cup poured by the planet thousands of years ago. Even the sediments at the bottom speak softly of these ancient transformations. Cores pulled from the dragon hole show alternating dark and light bands, each one representing a shift in climate. The darker layers are rich in organic carbon, deposited during warm, productive periods when plankton thrived and fell to the seafloor. The lighter ones are composed mostly of carbonate dust from colder, barren times when the ocean quieted. These bands repeat with almost hypnotic rhythm, marking the slow heartbeat of the Earth's climate. Some layers contain volcanic ash, blown across continents by eruptions whose names no one remembers. Each flake of ash, each grain of sand, each molecule of trapped carbon dioxide is a whisper from a sea that no longer exists. Among the most surprising discoveries in these sediments are microtectites, tiny glass spheres formed when meteorites struck the ocean millions of years ago. They tell of cosmic events that momentarily rewrote the chemistry of the seas, triggering changes in temperature and circulation that rippled for centuries. The fact that such traces lie preserved here shows how long the dragon hole has been collecting the planet's memories. It's not just a record of the ocean, but of the sky, the land, and the forces that shape them all. The fossils of coral and shell reveal more than biology. They record motion. As coral grows, it aligns its skeleton with the direction of sunlight and current. By studying those alignments in fossilized reefs, scientists can reconstruct the positions of ancient coastlines and even the tilt of the Earth's axis at the time. The corals trapped in the walls of the dragon hole are tilted slightly off vertical, a sign that the region has shifted slowly over thousands of years under tectonic pressure. The hole itself, then, is a kind of needle on a planetary seismograph, silently recording the Earth's slow movements. Its shape and orientation tell of continents drifting, of crust bending, of the ceaseless rearrangement of land and sea. And still, the whispers continue. Even now, the chemical reactions inside the hole are producing new minerals, gypsum, aragonite, calcite, that will one day be the fossils of our own time. They form slowly, coating the walls with thin films that trap the trace elements of modern seawater. Centuries from now, those films will harden into stone, locking in the record of today's atmosphere, today's temperature, today's pollution. Our presence, though invisible down here, is already being written into the future geology of the whole. The ancient seas spoke through coral, ours will speak through carbon. For the scientists who spend their lives studying this place, these discoveries are more than data. They are conversations across time. When they lower sensors or extract cores, they're not just measuring, they're listening. The results appear as graphs and charts, but behind each line is a voice from the deep past, the whisper of a warmer ocean, the echo of a glacier collapsing into the sea, the sigh of volcanic dust settling onto calm water. The dragon hole doesn't shout its history. It murmurs it in chemistry, in texture, in the patient layering of worlds. There's something humbling in realizing that the hole predates every human story, that it remembers climates older than language and tides older than memory. We're used to thinking of the sea as timeless, but even it has its eras, its beginnings and endings, its floods and droughts. The dragon hole has lived through them all. It was a cave before it was an ocean, a reef before it was a cave, a sunlit meadow of coral before it was darkness. Each stage left something behind, a whisper preserved in stone and water. Standing on the deck of a research vessel above it, surrounded by modern instruments and digital readouts, it's easy to forget how small our timeline is compared to what lies below. The dragon hole has outlasted every empire, every language, every shift of the shoreline. It has watched the planet cool, warm, flood, and freeze again. Its whispers remind us that the world we know is just one page in a much larger story. The seas before ours left messages in its walls. The sea we live in now will leave its own, and long after we're gone, when new oceans rise and new reefs grow, those whispers will still echo faintly in the stone, soft, patient, and eternal, telling whoever listens what the earth once was. At first, there is no visible difference. The water looks the same, still and heavy, its surface reflecting the faint shimmer of light from above. But as a sensor descends deeper into the dragon hole, the readings begin to change. Dissolved oxygen drops steadily. Then suddenly, at a certain depth, it falls to zero. Below that point, there is no breath left for creatures that rely on it. The water becomes anoxic, stripped of the invisible gas that fuels almost all complex life. It is not poison in the traditional sense. It is absence, the quiet suffocation of chemistry. To the fish, the crustaceans, the corals, oxygen is not optional. It is the difference between movement and stillness, between life and dissolution. When it's gone, the rules of biology change completely. In the upper layers of the dragon hole, oxygen still moves freely. Waves mix air into the sea, and plankton release it during photosynthesis. There, life behaves as we know it. Fish swim, microorganisms drift, and chemical reactions proceed at familiar speeds. But that liveliness fades quickly. Around 100 meters down, the water's density increases, isolating it from the surface. Currents no longer mix. Bacteria and decaying organic matter consume the remaining oxygen, leaving none to replace it. The transition is sharp, a boundary so precise it might as well be drawn with a knife. Above, the water breathes. Below, it holds its breath indefinitely. In most parts of the ocean, such anoxic zones exist only temporarily, balanced by upwelling currents or seasonal shifts. But here, sealed inside this vertical labyrinth, the balance never resets. Once the oxygen is gone, it stays gone. Every bit that enters through diffusion is consumed almost instantly by microbial activity. In effect, the deeper layers are locked in time, a stagnant reservoir that hasn't felt a breath of air in centuries. What continues to live there does so by rewriting the basic code of metabolism. Without oxygen, organisms turn to other elements for energy. Sulfate replaces oxygen as an electron acceptor, producing hydrogen sulfide as a byproduct. The smell of that gas, when samples are brought to the surface, is sharp and unmistakable, a reminder that the chemistry below would be fatal to us. Down there, however, it's the foundation of life. Sulfate-reducing bacteria thrive in the darkness, forming dense mats along the limestone walls and within the sediment. They are the recyclers of this silent world, breaking down organic matter molecule by molecule, releasing nutrients that feed other microbes. Their metabolism is slow, efficient, and ancient. It resembles the kind of life that existed on Earth before oxygen filled the atmosphere billions of years ago. This connection to the deep past is what fascinates biologists most. Studying the dragon hole's anoxic layers is like travelling back to a time before modern life evolved, when Earth's oceans were rich in iron and sulfur instead of oxygen. The bacteria that dominate here are analogues to those early pioneers, organisms that learned to survive by using what little energy chemistry could offer. They represent the persistence of that original evolutionary strategy, proof that even as the rest of the planet changed, small pockets of ancient conditions remained. The dragon hole isn't just a geological relic, it's a biological time capsule, preserving ecosystems that mirror the world's first seas. When scientists analyse water from these depths, they find an abundance of hydrogen sulfide, methane, and dissolved metals like iron and manganese. These compounds form as bacteria strip electrons from the surrounding rock, creating slow-motion chemical weathering. The process not only sustains life but reshapes the environment. Over time, layers of mineral deposits accumulate on the walls, thin films of black and grey metal sulfides that glimmer faintly under light. In some places, they've grown thick enough to change the reflectivity of the rock, producing the darker bands visible on sonar scans. The hole, in effect, records its own breathlessness in stone. The absence of oxygen also affects how sound travels. Normally, in oxygenated water, bubbles and microcurrents scatter acoustic waves, giving sonar a clear echo. In the anoxic zone, the water is denser, more uniform, and eerily quiet. Sonar signals travel farther but with less reflection, making the space feel vast and hollow. Submersible operators describe it as descending into silence, an environment where even machinery seems to fade. Without oxygen, not only does life vanish, but sound itself begins to die. And yet the anoxic layer isn't empty. It's populated by life forms adapted precisely for this condition. Some bacteria form symbiotic partnerships, sharing byproducts in tight chemical cycles. Others use trace amounts of nitrate or iron instead of sulfate, filling ecological niches invisible to the naked eye. There are also viruses, simple, parasitic entities that infect the bacteria and keep their populations in balance. This microbial warfare, unseen but constant, prevents any single species from overwhelming the system. It's an entire web of life operating without the need for air, relying only on reactions between rock and water. There's a strange kind of beauty in that. The absence of oxygen doesn't end life, it clarifies it, reducing existence to its essentials: energy, chemistry, structure. Without the comfort of oxygen, everything becomes deliberate. Growth slows, metabolism adjusts, waste turns to resource. Nothing moves fast enough to be wasteful. This slowness creates stability. The anoxic layer has remained chemically consistent for centuries because its inhabitants live within tight, self-regulating limits. They don't expand beyond what the system can sustain. They are the perfect citizens of scarcity. To study them, scientists deploy rovers that collect water in airtight chambers to prevent contamination. Each sample, when lifted to the surface, is handled like a fragile relic. Exposure to oxygen would instantly kill many of the microbes within. Researchers work quickly, transferring the water into sealed containers, preserving its ancient chemistry. Under microscopes, they observe filaments of bacteria forming networks across grains of sediment, connecting like wires in a circuit. These networks pass electrons directly from cell to cell, conducting energy through the mud. It's an elegant adaptation, one that mimics the principles of electricity long before humans discovered it. The dragon hole's oxygen-free depths have been running their own form of current for millennia. The most haunting part of this system is its quiet resilience. Once oxygen disappears, reintroducing it can be catastrophic. In similar environments elsewhere, when oxygenated water has accidentally mixed with anoxic layers, massive die-offs occur. Hydrogen sulfide reacts with oxygen to produce acid, killing everything that relies on delicate chemical balance. In the dragon hole, such mixing is rare thanks to its stable density layers. The separation between the oxygenated and anoxic zones is so strong that they exist side by side without touching, like two worlds sharing the same space. The interface between them is a literal line of life and death, a shimmering barrier where energy flows and life switches forms. That boundary fascinates scientists. They call it the redox cline, the zone of transition where oxygen fades and sulfur takes over. Here, the two worlds overlap briefly. Specialized microbes gather along this narrow band, exploiting the difference between chemical states. They act as brokers, shuttling electrons between oxygen-rich and oxygen-poor environments, connecting the upper sea to the depths below. These organisms are living bridges between atmospheres, mediating the exchange that keeps both layers stable. Without them, gases would build up unchecked, and the hole's chemistry would collapse. It's a reminder that even in separation, systems remain connected, each depending on the other to exist. When you think about it, the story of the dragon hole's oxygenless depths isn't about death at all. It's about endurance. The ocean, like the planet itself, always finds ways to use what's left. Where oxygen runs out, sulfur takes its place. Where energy seems exhausted, new pathways appear. The system reorganizes, rewrites its rules, and continues. The creatures above live by breath. The ones below live by reaction. The only constant is the will to persist. And so the whole remains divided. Two oceans in one. The living blue above, full of light and motion. The dark chemistry below, slow and silent. Between them, a delicate line marks the point where life changes form but not purpose. It's a lesson written in water. Even when oxygen runs out, the story doesn't end. It just begins again under different rules, spoken in the quiet language of the deep. If you could peel back the seafloor beneath the dragon hole, you'd find that the ocean doesn't end where the water meets stone. Beneath the visible abyss lies another network, unseen but immense, an entire underworld of liquid that moves through rock, sand and fissure as quietly as breath through lungs. These are the hidden rivers of the ocean, vast veins of groundwater that pulse beneath the seabed, connecting coastlines, trenches and reefs in ways that even the most advanced instruments can barely trace. They aren't rivers in the sense we know them. There are no banks, no current that carries driftwood or fish, but they flow all the same, creeping through the porous skeleton of the planet at speeds too slow for the human mind to imagine. In the dragon hole, this secret plumbing reveals itself in subtle ways. Fluctuations in salinity, unexplained changes in temperature, the faint rise of minerals that can't be accounted for by the surrounding sea. When scientists first lowered sensors into the dragon hole and mapped the gradients of its layers, they noticed something that didn't fit. Near the base, where the pressure is immense and oxygen long gone, there were sudden shifts in the chemistry of the water, tiny but consistent pulses of fresher, cooler fluid pushing upward through the sediment. It wasn't surface seawater sinking. The isotopic signatures were wrong. This was water that had been sealed away within the rock for centuries, even millennia, slowly escaping through microscopic cracks. The hole, it turned out, wasn't just a pit in the ocean. It was an opening in a much larger network, a spring where Earth's internal waters quietly return to the sea. Submarine groundwater is one of the planet's least understood systems. Beneath every ocean floor lies a labyrinth of cavities and porous layers where fresh water and salt water mingle. It's not static. Driven by pressure, temperature and tectonic motion, these hidden rivers move constantly, though at a pace measured in centimetres per year. They flow under continents, between islands, and through the foundations of reefs like veins through flesh. Some emerge at hydrothermal vents, heated and mineral-rich. Others, like the ones feeding the dragon hole, travel in silence, cold and slow, unlit and unseen. They are the Earth's way of circulating memory, transporting the chemical imprints of land to sea, of mountain to abyss. When researchers take samples from the lower levels of the dragon hole, they find isotopic traces of terrestrial minerals, strontium, lithium, and silicates, elements that don't belong in pure seawater. These elements indicate the presence of groundwater that once flowed through continental crust, dissolved rock, and carried it into the ocean's hidden plumbing. Somewhere far away, rain that fell on land centuries ago seeped downward, filtered through stone, and has only now re-emerged here at the bottom of a blue hole in the South China Sea. That connection between sky and abyss is almost impossible to picture, yet it's real. The water inside the dragon hole isn't only oceanic, it's a blend of worlds, a meeting place for rain, rock, and sea. To understand how this works, imagine the Earth as a sponge rather than a solid sphere. Beneath its surface, water fills pores and fractures, saturating everything down to the crust. When pressure changes due to tectonic shifts, tides, or even changes in barometric weight, those fluids move. They push upward through cracks, seeking release. Blue holes, caves, and submarine springs are the points where that hidden circulation breaks through into visibility. The dragon hole is one of these vents, though not explosive or volcanic like those at mid-ocean ridges. Its rivers move slowly, invisibly, carrying chemical whispers from the deep interior. At the microscopic level, the rock beneath the hole is alive with movement. Pores in the limestone hold trapped water that creeps through capillary channels no wider than a hair. Inside those channels, minerals dissolve and reprecipitate in endless cycles. Bacteria colonize them, feeding on trace nutrients and leaving behind biofilms that alter the permeability of the rock. Over centuries, these microscopic interactions carve out new paths, expanding narrow pores into conduits large enough for fluids to migrate. The process is glacially slow but relentless. The hidden rivers do not erode like surface ones. They dissolve and rebuild simultaneously, constantly adjusting their own routes. The movement of these subsurface waters has profound consequences for the dragon hole's chemistry. The fresh inflow from beneath introduces new elements: iron, manganese, phosphates, that act as nutrients for microbial life. Even in the absence of sunlight, these inputs sustain the abyssal ecosystem. It's a quiet form of upwelling, but inverted. Instead of nutrients rising from deep ocean currents, they rise from within the planet itself. The microbes that live in the anoxic layers depend on this steady trickle of minerals, using them to drive chemical reactions that produce energy. Without those hidden rivers, the ecosystem would starve. Seismic imaging has revealed something even more remarkable. Beneath the dragon hole, the limestone platform isn't solid. It's riddled with voids and tunnels extending laterally for kilometers. Some of them connect to other sinkholes or cave systems across the Paracel region. The dragon hole may not be a solitary structure at all, but part of an underground network, a drowned landscape of passageways carved when sea levels were far lower. When the ocean returned, those passages became conduits for water exchange between surface and subsurface. The result is a dynamic system that blurs the line between ocean and aquifer. The hidden rivers don't simply feed the hole, they define it. On long enough timescales, these underground flows may influence the ocean itself. By carrying dissolved minerals from the crust, they contribute to the global salt balance and the cycling of carbonates that regulate pH. The dragon hole, though small in comparison to the open sea, acts as a node in this planetary plumbing. Every molecule of water that seeps through its floor participates in a conversation that spans continents and ages. When scientists model global chemical flux, they have to account for these unseen contributions. Without them, the equations of the ocean don't balance. The presence of groundwater also explains one of the dragon hole's most intriguing mysteries: the faint temperature anomalies detected near its bottom. The water there is slightly cooler than expected given its depth and salinity. That chill isn't from currents above, it's from water rising slowly from below, water that has spent centuries in darkness, insulated by rock. As it seeps upward, it cools the surrounding layer, creating microcurrents that redistribute minerals and gases. These movements are small, but over millennia they shape the hole's internal structure, renewing it from within. What's striking is how seamlessly this invisible system connects to the rest of the planet. The rain that falls on distant mountains eventually becomes part of these hidden rivers. It moves underground, joins the ocean, rises again through holes like this one, and evaporates back into clouds. The same droplet may spend 1,000 years beneath the surface before it returns to the sky. In that sense, the dragon hole is not a boundary but a waypoint, a quiet exchange point in the endless recycling of water. The hydrologic cycle we learn in school, with arrows moving from ocean to cloud to land and back, is only half the story. The other half happens here, beneath our feet, in the places we can't see. During expeditions, when researchers deploy tracers to follow these subterranean flows, the results sometimes defy expectation. Injected dyes or isotopes disappear into the rock and reappear weeks later miles away, carried by hidden currents that ignore our maps. It's a reminder that the Earth's architecture is more porous and alive than it seems. Even the most static landscapes are full of motion if you look closely enough. For the life in the dragon hole, those hidden rivers are lifelines. For the scientists studying them, they are proof that the planet's systems are more integrated than we often imagine. And for anyone who stands above the hole, watching the surface remain calm while unseen water moves beneath, they are a humbling metaphor. The ocean's deepest mysteries aren't always in the open abyss. They're in the quiet spaces where land and sea overlap, where fresh water whispers through salt, and where the world keeps renewing itself without ever asking to be noticed. Somewhere under the dragon hole, water that fell as rain before the dawn of recorded history is still making its way upward, molecule by molecule, to join the modern ocean. When it finally reaches the surface, it will have carried with it the imprint of continents, the memory of stone, and the chemical breath of time. That, perhaps, is the truest form of continuity this planet knows. The slow circulation of water through every possible state, linking everything that has ever lived. And deep below the sea, those hidden rivers will continue to flow, unseen but unstoppable, keeping the heart of the ocean quietly beating beneath the silence. When scientists peer into the dragon hole, they aren't just looking at an isolated pit in the ocean. They're staring into a place where extinction and survival share the same thin boundary. It is, in every sense, a vault of endings and continuations. The conditions inside it, oxygenous, pressurized, sealed, are not simply hostile, they're selective. Over the millennia, this vertical world has witnessed countless lineages rise and vanish, their remains preserved in the slow rain of sediment that coats its bottom. Yet among the traces of what once lived, life still persists. Every sample pulled from the depths carries evidence of both, the silence of extinction and the persistence of survival woven into the same handful of mud. The dragon hole isn't a grave. It's a biography of the planet's endurance written in chemistry. When the first detailed cores were lifted from its floor, scientists expected only mineral layers and ancient dust. What they found instead were microfossils, plankton, diatoms, and bits of shells from species long extinct. Each layer of sediment was like a chapter of history, marking shifts in the ocean's temperature, acidity, and productivity. The deeper they dug, the older the world became. Some of the shells belonged to species that vanished when sea levels fell after the last interglacial. Others to creatures that disappeared when the atmosphere began warming again thousands of years later. Each extinction event, large or small, left behind a thin band of difference. Darker sediment, altered isotope ratios, a sudden absence of particular forms. Those fossils are not just records of death, they're indicators of adaptation. Around each extinction layer are traces of recovery, new forms appearing, new chemical balances stabilizing. In the dragon hole, these transitions happen in microscopic detail, preserved more perfectly than anywhere else because the anoxic water prevents decay. Without oxygen, organic matter doesn't decompose, it fossilizes. Pollen from ancient plants, fragments of DNA from plankton, even traces of bacterial lipids endure in the cold, dark mud. Each one is a survivor of oblivion, carrying information about how life responded when the planet changed. To hold a fragment of that sediment is to hold a story of collapse, followed by persistence. Every major climate shift the Earth has known has left its echo here. The sediment cores contain evidence of cooling events where productivity plummeted, times when the surface ocean became too stratified for nutrients to circulate. Then, above those barren layers, come richer deposits, where microbial mats flourished again, signalling recovery. These cycles mirror global extinction patterns: stress, collapse, adaptation, resurgence. The Dragon Hole is a miniature version of Earth's broader history, compressed into meters of mud. It is proof that life never stops adjusting, no matter how hostile the environment becomes. Somewhere between the extinction layers, scientists have found genetic material from microorganisms that still exist today. Their ancient ancestors survived all those changes, enduring ice ages and heat waves, fluctuations in salinity and chemistry, without ever leaving their narrow ecological niche. These lineages have outlived entire ecosystems by simply refusing to evolve beyond what works. They are the minimalists of evolution, unchanged because they never needed to change. The Dragon Hole is their refuge, a sanctuary where the outside world's chaos barely reaches. Among the preserved microfossils are also clues to events of global significance. Tiny spikes in iridium concentration mark moments when meteorite dust settled across the oceans. Elevated sulfur isotopes suggest massive volcanic eruptions that darkened skies and acidified seas. Even the faint traces of radioactive isotopes left by human activity in the 20th century have begun to appear in the uppermost layers, marking the newest and most fleeting chapter of extinction and survival. The hole quietly records it all, without judgment, without pause. Above the sediment, within the water column itself, a more immediate story unfolds. In the upper layers, plankton thrive briefly before sinking into the darker zones. Some species persist year after year, adapting to slight changes in salinity or temperature, while others disappear from samples entirely, replaced by more tolerant forms. This turnover, invisible from the surface, is a continuous process of natural selection. The Dragon Hole's stratified environment acts as an evolutionary laboratory, each layer a separate world testing different survival strategies. Where oxygen remains, aerobic microbes dominate. Where it vanishes, anaerobes take over. No single form wins forever. Every boundary is a negotiation between persistence and extinction. There are parallels here with the great die-offs that reshape the planet. The conditions that define the Dragon Hole, oxygen loss, acidification, isolation, mirror what oceans experienced during ancient mass extinctions. The Permian, the Triassic, even parts of the Cretaceous all saw similar chemistry. Seas turned stagnant, oxygen vanished, and sulfur took its place. In those eras, most marine species died, but not all. Bacteria, archaea, and the simplest life forms endured, evolving to use sulfur and iron as their energy source, just as they do here today. The Dragon Hole is, in that sense, a model of both apocalypse and recovery. It shows what the ocean becomes when it stops breathing, and how life still finds a way to inhale differently. Modern scientists watch this with more than academic interest. The spread of oxygen-depleted zones in today's oceans has become a warning sign of environmental stress. As climate warms and circulation slows, regions like the Dragon Hole are no longer rare. They are multiplying. What was once a window into Earth's distant past may also be a glimpse of its future. The microbes thriving in the anoxic depths today could be prototypes for the organisms that will dominate the oceans tomorrow if oxygen continues to decline. The Dragon Hole doesn't just echo extinction, it foreshadows it. But extinction never tells the whole story. Even as the deep layers remain toxic, the upper zones continue to bloom with new life. Coral larvae settle along the rim, algae colonize the sunlight, small fish hover at the edges. The boundary between death and vitality is sharp but close. If the hole teaches anything, it's that survival isn't about escaping catastrophe. It's about existing within it. Every layer of its depth, from the sunlit surface to the black sediment floor, holds proof that life adapts faster than destruction completes its work. When divers look down into the dragon hole, they see darkness. But that darkness isn't emptiness. It's memory. It holds every extinction the Earth has endured, every recovery that followed, all compressed into one silent column of water. The fossils and genes it preserves are like echoes, muted repetitions of ancient events still resonating today. To study them is to hear those echoes faintly, a reminder that extinction and survival are not opposites but partners. One clears the space, the other fills it again. Somewhere at the bottom, in the oldest mud, are fragments of organisms whose descendants still swim in the surface sea above. Their lineage has crossed ice ages, droughts, and chemical upheavals without ever knowing it. The water that once drowned their ancestors now nourishes their kin. That continuity is the quiet defiance of life, the refusal to vanish completely. In the dragon hole, where extinction and endurance intertwine, you can almost feel that defiance still humming in the dark, a low patient echo that says, "I am still here." There's a sound beneath the ocean that isn't a sound at all. It's too low, too slow, too ancient for ears to catch. It isn't the crash of waves or the hum of whales or the scrape of currents across coral. It's the breathing of the planet itself, a vast geological exhale that began long before language, long before anything alive had lungs to name it. Inside the dragon hole, that breath is trapped. The air that once filled its upper caverns, the gases still rising from its depths, and the faint movements of water through its hidden veins, all of them carry echoes of the Earth's earliest respiration. Listening to them is not an act of hearing in the usual sense. It's a matter of interpretation, of learning to read pressure and chemistry as if they were sound waves. What scientists detect in those quiet oscillations is, quite literally, the planet breathing through stone and water. The first time researchers placed hydrophones deep within the dragon hole, they didn't expect to find anything. The environment seemed too still for noise. Yet the recordings they retrieved were full of patterns, low-frequency hums and pulses, irregular but persistent, sometimes rising, sometimes falling with the tide. At first, they suspected mechanical interference from the submersible, or distant ships, or seismic activity. But after careful filtering, they realized these vibrations came from within the hole itself. The sound was generated by the movement of trapped gases, slow seepage through porous limestone, and subtle shifts in pressure as the surrounding ocean expanded and contracted with temperature changes. It wasn't static. It had rhythm, like breath. Those pulses match what oceanographers call internal waves, oscillations that move not along the surface, but between layers of different densities. In the dragon hole, these internal tides push and pull along the boundaries of salt and temperature, causing minute compressions and relaxations in the water column. The hole's geometry amplifies them, creating a natural resonator. Each movement of the sea above translates into a vibration below, echoing through the limestone like wind through a pipe organ. The frequency is far too low for human hearing, cycles measured in minutes, sometimes hours, but when sped up electronically, the recordings sound almost alive, a deep, slow murmur that seems to breathe. For geophysicists, these patterns are more than curiosity. They provide data about how the planet moves. Every tremor, every sigh of pressure through the stone reveals information about Earth's crust, tides, and even climate. By studying the dragon hole's acoustic signatures, scientists can detect distant earthquakes, track how energy travels through ocean basins, and map the hidden architecture of the sea floor. The hole acts as a natural stethoscope pressed against the planet's chest, amplifying the faint beats of geological life. What it records isn't noise, it's the story of motion written in frequency. But beyond the scientific precision, there's something deeply human about calling it a breath. The gases that seep from the rock are, in a literal sense, the remains of ancient atmospheres. Long before plants oxygenated the planet, Earth's air was dominated by carbon dioxide, methane, nitrogen, and water vapour. Those gases dissolved into early oceans, became trapped in sediments, and were later locked away as minerals. Over millions of years, tectonic shifts and groundwater flows have released them again, molecule by molecule. The faint streams of gas rising from the floor of the dragon hole may well be the same carbon that once drifted through primordial skies. When those bubbles reach the surface and break, the planet exhales the past. It's humbling to think that each bubble, tiny and transient, carries the memory of a world that no longer exists. Scientists analyse their composition with mass spectrometers, isolating traces of methane, hydrogen sulfide, and rare isotopes of carbon and oxygen. From those readings, they reconstruct the age and origin of the gas, tracing its journey through rock layers that predate humanity by tens of millions of years. The oldest samples suggest that some of this trapped carbon has been circulating since before mammals appeared. The dragon hole, in that sense, is not just breathing, it's remembering. Every exhalation is a message from deep time. The water itself participates in this respiration. When internal tides rise, they carry gases upward. When they fall, those gases dissolve again. The exchange happens slowly, quietly, like the expansion and contraction of a chest. This constant motion maintains the hole's delicate chemical balance. Without it, gases would accumulate, poisoning the system. Instead, the water releases and absorbs in turn, regulating its own atmosphere just as the Earth does. The balance is so fine that even small changes in temperature or salinity can alter the rhythm. To measure those fluctuations is to listen to the pulse of equilibrium, a breathing pattern sustained for millennia. There's also a more literal connection between this deep respiration and the air we breathe above. Carbon dioxide released from submarine vents and seeps eventually diffuses into the atmosphere, contributing to the planet's long-term carbon cycle. The dragon hole's emissions are tiny compared to volcanoes or continental shelves, but over thousands of years they add up. Some of the carbon in the air you inhale right now may once have risen from the limestone beneath that blue circle of sea. The exchange between abyss and sky is continuous, linking the oldest breath of the earth to the newest one in your lungs. When acoustic sensors pick up low rumbles, they also catch the echoes of distant storms. Waves breaking hundreds of kilometres away send pressure waves that travel through the water column and concentrate in the hole's narrow throat. These vibrations mingle with the internal tides, creating interference patterns that shift with the seasons. The hole becomes a recording device not just for its own breath, but for the ocean's entire body. Each year's storms, each quake, each subtle current change leaves an imprint in the acoustic record. Listening to it is like eavesdropping on the planet talking to itself. To make sense of such data, scientists often compress time, accelerating the recordings by thousands of times. In those sped-up sounds, something extraordinary happens. The frequencies align into audible tones, deep and resonant, sometimes harmonic. You can hear the dragon hole's shape in those tones, the resonance of its chambers, the curvature of its walls. It becomes a voice, though not a human one. Some describe it as a hum, others as a sigh. But perhaps it's better to think of it as the planet's oldest language, one that predates words and music. Every rock, every ocean, every gust of wind has been speaking it since the world cooled. We just rarely slow down enough to listen. The idea of the Earth breathing might sound poetic, but it's rooted in physics. The planet expands and contracts minutely with tides, with changes in pressure, with the subtle heating and cooling of its crust. That movement shifts entire oceans by centimetres every day, enough to alter gravity ever so slightly. The dragon hole, with its sensitivity to density and resonance, records those shifts faithfully. Its sensors detect pressure variations caused by lunar cycles, weather systems, even the migration of masses within the mantle. In that way, the hole functions like a barometer for the whole planet's respiration. When scientists graph its data, the result looks like a heartbeat, steady oscillations interrupted by spikes of disturbance, like inhalations and exhalations recorded over time. For those who work there, the hole's breath becomes strangely familiar. After months of studying data, they begin to anticipate its rhythm. They can tell when tides are strong or when a distant storm is approaching simply by watching the frequency curves change. Some describe a kind of quiet companionship in that rhythm, a sense that the Earth, for all its vastness, is not inert but alive in a way we can measure. To listen to those oscillations is to feel the pulse of something that existed long before us and will continue long after. At night, when the sea is calm and the instruments hum softly, the surface of the dragon hole looks perfectly still. But deep below, invisible movements continue, gases rising, layers shifting, vibrations passing through stone. The planet exhales through its oldest lung, each breath measured in centuries. We can't hear it without machines, but it's there, a sound too patient for the human timeline. In that slowness lies something profoundly comforting. The Earth keeps breathing, no matter how much we change its surface. It breathes through water, through cracks, through ancient stone. And if we listen carefully enough through science and silence alike, we might just recognize that its oldest breath has never stopped. There's something almost unreasonable about how humans respond to depth. We are surface creatures, made for light and air, yet the darker and more unreachable a place becomes, the more we want to go there. No one needs to tell us why. The urge to descend, to look over the edge of what we understand and imagine what waits below, is built into us as completely as hunger or sleep. The dragon hole embodies that pull better than almost any place on Earth. It doesn't offer riches or safety or even comfort. It offers silence, distance, and the promise of something that can't be seen. And for reasons that defy logic, that promise is enough. Every expedition, every instrument lowered into its depths, every diver who risks the crushing pressure to glimpse its walls is answering a call that feels older than reason. The human pull toward depth isn't just curiosity. It's a kind of gravitational emotion, a need to reach downward as though some part of us recognizes the dark as home. That pull begins long before anyone steps onto a boat. It starts with maps, with the simple act of seeing a circle of deeper blue surrounded by shallower sea. The shape alone sparks imagination, a perfect void in a world that otherwise overflows with noise. The first people who sailed near the Paracel Islands must have noticed how the water changed colour, how sound seemed to drop away, how birds avoided the spot. Even without instruments, they must have felt that there was something different here. Depth announces itself not by sight, but by atmosphere. It exerts a psychological weight, pressing on thought the same way pressure presses on the body. To know that something continues downward without end is to feel both awe and unease. Modern divers describe that feeling as a paradox. The deeper they go, the more alien the world becomes, yet the more they feel compelled to continue. At a certain point, descent becomes less about exploration and more about surrender. The light fades, sound narrows to the hiss of air in the regulator, and the body begins to sense the water not as an obstacle but as part of itself. For those who've reached the limits of the dragon hole's upper chambers, there's a moment when the dive stops being about discovery and becomes about proximity, about being near something that resists definition. They speak of a quiet that feels alive, of pressure that feels intimate, of a darkness that doesn't threaten so much as absorb. That's what depth does. It removes the unnecessary until all that's left is awareness. This pull has always defined exploration, even beyond the sea. The same instinct that drives divers into the dragon hole once drove astronomers to look through telescopes and miners to dig tunnels into mountains. It's not about conquest, it's about contact. Humans seek the edge of their environment not to escape it, but to feel it more completely. The ocean, with its layers and silences, is the ultimate edge. Close enough to touch, but vast enough to remain unknowable. When the first submersible descended into the Mariana Trench, one of the pilots reportedly said he felt a strange familiarity in the darkness, as if the void wasn't hostile but simply indifferent. That indifference is part of the draw. The deep doesn't care about us, and that makes our presence there feel real in a way few other experiences can. In the Dragon Hole, that feeling intensifies. There are no grand rock formations or schools of bright fish, no dramatic scenes of undersea life. There's only shadow, pressure, and the slow realization that you're inside something ancient and self-contained. It isn't beautiful in the traditional sense, yet it provokes reverence. The deeper a person goes, the more irrelevant the idea of purpose becomes. Depth strips away context. It doesn't tell you what you're looking for. It makes you confront why you're looking at all. Some divers emerge with data, others with silence, but all of them come back changed in ways they can't explain. It's not enlightenment, it's recalibration. The hole reminds them that the world's greatest presence is often found in its absences. Psychologists studying deep-sea behaviour have a term for this pull, the abyssal drive. It's a mix of curiosity, thrill and surrender. A mental state that arises when the mind recognises both danger and mystery. The drive isn't unique to explorers, it's part of the human condition. We chase emotional depths the same way we chase physical ones. Grief, love, solitude, obsession. All versions of descent into something larger than ourselves. The Dragon Hole just makes that metaphor literal. Every dive into it mirrors the inward dives we take into memory or thought. Those moments when silence becomes confrontation and stillness becomes revelation. The physical dangers of that pull are real. Divers who push too far face nitrogen narcosis, a kind of intoxication that turns euphoria into confusion. The body forgets which way is up, and the mind, detached from air and light, starts to drift. Some describe hearing whispers, a low resonance that might be blood pulsing through the ears or the hum of pressure on the skull. It's the same illusion that once convinced sailors that sea spirits lived in holes like this one. The Dragon Hole amplifies that sensation because of its perfect shape. Sound spirals inward, echoing against the walls until it feels as though the water itself is speaking. To those who've descended far enough, that voice becomes real, a vibration of both physics and imagination. And yet, despite the danger, people keep returning. Every generation builds better instruments, stronger suits, more sophisticated sensors, but the motivation stays the same. The descent isn't about utility, it's about contact with something that makes us small. The hole's darkness reminds us of proportion. How thin the line is between exploration and erasure, between knowing and being lost. To face that and keep descending anyway is an act of faith disguised as science. The divers call it curiosity, but what they're really chasing is belonging, a sense that somewhere in that crushing stillness we're touching the same forces that shaped us. This attraction to depth also has a quieter side. Even those who never dive feel it in subtler ways. The fascination with maps of the ocean floor, the pull of stories about lost ships, the comfort of staring into dark water. Depth invites reflection because it's both literal and metaphorical. To look down into it is to see the physical representation of mystery itself. The Dragon Hole becomes a mirror not of the sea but of our own internal landscapes, the parts of the mind that stay hidden until something draws us into them. For the scientists who spend their lives studying this place, the pull becomes something close to devotion. They talk about the Dragon Hole not as an object but as a presence, an entity that demands patience and humility. Its data, they say, comes slowly, reluctantly, as if the abyss offers knowledge on its own schedule. To work here is to accept that progress will be measured in millimeters and years. Every reading taken, every core extracted, is a small victory against vast indifference. yet none of them stop. The deeper they study, the more they realise that understanding the whole means understanding the human instinct that created the study itself. The drive to descend, to ask questions that can never be fully answered. That instinct doesn't fade with technology, it evolves. The submersibles get quieter, the cameras sharper, but the feeling remains the same as it must have been for the first person who peered into the dark water and felt their breath catch. The dragon hole offers no comfort, no treasure, no resolution. It offers a question shaped like an abyss. How far are we willing to go to meet what we don't understand? The answer, if history is any guide, is always the same, as far as it takes. Because in the end, depth isn't just something the Earth contains, it's something the human mind creates. The dragon hole simply gives it a form. It is the physical echo of our need to search downward, to find meaning in what resists explanation. Every diver who descends, every scientist who studies, every listener who imagines what it must look like down there is responding to that same ancient pull, the need to stand at the edge of the known and lean in to touch the silence that built us, and to feel, if only for a moment, what it means to belong to something deeper than ourselves. No matter how much we learn about the ocean, the question keeps resurfacing. Why do we keep going back down? Why do we keep sending ourselves into pressure and silence, into places where no sunlight reaches and no guarantee of return exists? The dragon hole, with all its data and mystery, forces that question every time someone peers over its edge. We have mapped it, measured it, named its layers, and still we descend. Some come with instruments, others with cameras, a few with nothing but the will to see what lies below. It isn't just curiosity anymore, it's compulsion. For as long as there has been depth, there has been the desire to enter it. And the deeper we go, the harder it is to explain why. Every expedition begins with the same ritual: preparation, calculation, calibration. The science is meticulous. Pressures are measured, gas mixes tested, safety margins confirmed. Everything is designed to minimize risk. Yet when the moment comes to actually descend, logic recedes. The divers describe it as a kind of surrender, a letting go of everything familiar. The surface disappears. Sound changes, light folds, time stretches. The deeper they go, the less the world above seems real. There's a moment when gravity reverses in the mind and descent becomes flight. And at the bottom of that feeling is the truth that no instrument can record. We keep diving down because down is the direction that still belongs to mystery. The human story has always been a vertical one. We build upward toward the sky and downward into the earth. Both directions promise something beyond reach, one light, the other dark, but the difference is that the upward climb is visible. We can see the stars we reach for. Downward, we have to imagine what we'll find. That act of imagination is powerful. It's the origin of myth and science alike. When early cultures told stories about underworlds and sea gods, they weren't describing geography, they were giving shape to the unknown. The dragon hole fits perfectly into that lineage. It is a modern underworld, not of fire or punishment, but of pressure and silence. To enter it is to repeat the oldest ritual humans know, to descend into uncertainty and come back changed. For scientists, the descent is about knowledge. Every meter adds another layer of data: salinity, temperature, isotopic ratios, microbial samples. Each number helps explain how the ocean works, how climate connects to chemistry, how ancient water still moves beneath the crust. But behind the graphs and instruments is something older than the scientific method. It's a feeling, an ache for contact with something unspoiled by human touch. The data is proof of our presence, but the silence beneath it is proof of something greater, a world that existed long before we learned to measure it. There's also the paradox of risk. The deeper we go, the closer we come to limits, the point where light vanishes, air thins, machinery strains, and human bodies begin to fail. And yet that very risk sharpens focus. It strips away distraction. In the face of depth, survival becomes attention. The divers who enter the dragon hole describe the experience as pure concentration. Every breath counts, every sound matters, every movement feels deliberate. It's a form of mindfulness born not from peace but from necessity. And when they surface again, gasping in the open air, they carry that stillness with them, a memory of clarity that the surface world rarely offers. But maybe the real reason we keep diving down is because we're looking for reflection, not discovery. The abyss isn't a foreign world. It's a mirror held up to the parts of ourselves we rarely see. In the dragon hole's darkness, stripped of distraction, a person is reduced to sensation, pressure, breath, heartbeat. The boundaries of identity blur. What remains is awareness, raw and quiet. The ocean doesn't speak, but it listens, and that listening changes those who dare to enter. It reminds us of proportion, of how small we are, of how much we depend on the unseen. In that humility lies something close to comfort. Every diver knows the temptation to go just a little farther. The instruments say stop, the gauges warn of danger, but curiosity whispers one more meter. That whisper isn't reckless, it's ancestral. It's the same impulse that drove our ancestors to cross deserts, climb mountains, and sail into uncharted waters. The ocean simply amplifies it. The dragon hole turns it into a literal descent, a physical enactment of the inward pull that defines humanity. To go down is to meet ourselves without noise, to see what remains when all the light has been stripped away. For those who study the hole from above, the compulsion is just as strong. They watch the data scroll across screens long after midnight, trying to interpret patterns that seem to move according to their own logic. The deeper the analysis goes, the deeper the questions become. Why does the salinity fluctuate so precisely? How can an ecosystem survive without sunlight or oxygen? Each answer spawns a dozen new mysteries. Knowledge doesn't quiet curiosity, it deepens it. The more we understand, the more we realize how much remains invisible. The descent never ends, it just shifts from physical to intellectual. There's another kind of descent too, one that isn't about science at all, but about meaning. For some, the dragon hole represents the unknown itself, the literal embodiment of what can't be conquered. In an age where satellites have mapped every mountain, an algorithm predicts every storm, the idea that something remains beyond comprehension feels almost sacred. The hole becomes a refuge from certainty, a reminder that mystery still exists. That may be the most human reason of all for returning. Not to solve the unknown, but to keep it alive. To descend into darkness and return is an act of balance. It mirrors the rhythm of breath, the rise and fall of waves, the cycle of sleep and waking. Down is not only where danger lies, it's also where renewal begins. Seeds grow underground before they break the surface. Roots dig downward to sustain what blooms above. Even thought itself moves in descent. We dive into memory, into dreams, into the subconscious. The dragon hole is a physical version of that inner geography. We dive because life itself is a series of descents and ascents, and somewhere in that motion we find meaning. Sometimes, late at night, after the research vessels have shut down their engines and the sea lies flat and unbroken, someone will stand at the edge of the deck and look into the blue-black circle below. There's no movement, no sound, just the illusion of endless stillness. Yet beneath that calm the hole continues, breathing, changing, whispering. It is everything we know and everything we can't reach, coexisting in one place. And staring into it, a person understands, even if only for a moment, why we keep diving down. Not for discovery, not for conquest, not even for knowledge, but for the quiet truth that the unknown is where we feel most alive. When the engines stop and the water settles into glass, the dragon hole looks like the calmest place on Earth. The circle of blue seems frozen in time, its edges blurred by heat and distance, its centre darker than shadow. Yet the longer you look, the more you realise it isn't still at all. The surface trembles almost imperceptibly, disturbed by the weight of light itself. Beneath that faint shimmer lies everything. The layers of salt and stone, the hidden rivers, the vanished life, the slow breath of the planet. And somewhere within that vertical silence, there's the sense of being observed. The dragon hole doesn't just sit quietly, it watches. Every descent, every instrument, every ripple at the surface becomes part of its memory. The silence here is not absence, it's tension. People often say the ocean is indifferent, but that's not quite true. Indifference is the absence of care, and the sea in its own way notices everything. It records temperature, gravity, light, and movement with perfect fidelity. It keeps every sound, every vibration, every change in chemistry. It knows when something enters it, and it adjusts around that presence like breath shifting in sleep. The dragon hole is the purest expression of that awareness. Its stillness is not passive, it's receptive. When a diver descends, the water closes over them like an eyelid, measuring weight and heat and pressure. Every pulse is felt, every exhaled bubble counted in silence. The ocean may not think, but it remembers. When the instruments send their signals back to the surface, when the cameras rise from darkness with hours of footage, what returns is only data. But behind those numbers is a kind of dialogue. The hole has answered each question in its own language. A change in salinity, a flicker of reflected light, a shift in pressure. Every experiment, every dive, every attempt to understand becomes a conversation with something vast and ancient. The silence that comes back is not emptiness. It's a response, one too slow and too deep for human senses to translate. We listen for it in the creak of the hull, in the rhythm of the waves, in the readings that change by decimals. We call it silence because we don't have a better word for the kind of awareness that doesn't need to speak. At night, when the last of the daylight drains from the horizon, the dragon hole becomes indistinguishable from the sky. The stars above and the darkness below mirror one another so perfectly that the line between them disappears. Standing on the deck of a ship, you can't tell where gravity begins. The hole becomes a second sky, one that swallows rather than shines. That reflection has always drawn people. The idea that the sea is both mirror and opposite of the heavens. We look upward for meaning, downward for truth, and both directions answer in silence. The dragon hole is where those silences meet. All the layers we've explored, the oxygen, the ancient gases, the microbial worlds, the architecture of stone and pressure, they converge here in a single still point. The deeper we've gone, the more we've learned that the abyss isn't an end but a continuity. Everything that falls into it, light, sound, memory, keeps moving, transformed but never lost. The dragon hole teaches that the unknown doesn't erase, it absorbs. Its silence is a form of memory older than words, a patience so complete that it seems like stillness. To study it is to confront the scale of our own noise. There's a quiet moment on every expedition when work stops. The instruments hang motionless, the crew rests, and the hole lies beneath them like an open eye. In that pause you can feel the size of what you've touched, a system older than weather, deeper than comprehension, perfectly content to exist without witness. You realise that the silence you've been listening into has also been listening back. Every vibration, every word, every breath sent into its depths returns transformed. The ocean is not a void, it's an echo chamber for existence. It takes in everything, softens it, and returns it as calm. We've spent centuries filling the planet with noise, engines, communication, movement, but places like this remain untouched, their silence intact. It's not the fragile silence of emptiness, but the durable quiet of understanding, the kind that doesn't need to compete or explain. That's why standing above the dragon hole feels less like observation and more like confession. The surface reflects not just the sky, but whoever looks into it. You can see yourself there for a moment, your shape distorted by light and gravity, and then the image dissolves. The whole keeps your outline as memory, another brief trace in the long ledger of attention it holds. Eventually the engines start again, the waves rise, the reflection breaks. The whole vanishes back into the continuum of the sea, leaving nothing visible behind. But its silence lingers. It stays in the ears of those who have heard it, in the pressure on their bones, in the data that continues to hum long after the ship has gone. It's a reminder that for all our instruments and curiosity, there will always be places that remain fundamentally unreadable. Not because they hide, but because they exist at a scale where comprehension itself dissolves. And maybe that's what we were meant to find. Not answers, not closure, but the awareness that the world is listening too. That beneath our questions, beneath our dissent, beneath our endless search for meaning, there is a silence watching back. Vast, patient and unbroken. It doesn't judge and it doesn't explain. It simply is. The dragon hole remains, as it always has been, the eye of the ocean, open and aware, keeping vigil over everything that moves above it. And long after we're gone, when the last of our signals fade and the sea folds back into itself, that silence will still be there, watching, remembering, breathing without end.